The following is a conversation with Andrew Huberman, a neuroscientist at Stanford, working to understand how the brain works, how it can change through experience, and how to repair brain circuits damaged by injury or disease. He has a great Instagram account at Huberman Lab, where he teaches the world about the brain and the human mind. Also, he's a friend and an inspiration in that he shows that you can be humble, giving, and still succeed in the science world. Quick mention of each sponsor, followed by some thoughts related to the episode. 8 Sleep, a mattress that cools itself and gives me yet another reason to enjoy sleep. SEM Rush, the most advanced SEO optimization tool I've ever come across, and Cash App, the app I use to send money to friends. Please check out these sponsors in the description to get a discount and to support this podcast. As a side note, let me say that I heard from a lot of people about the previous conversation I had with Yaron Brook about objectivism. Some people loved it, some people hated it. I misspoke in some parts, was more critical on occasion than I meant to be, didn't push on certain points that I should have, was undereducated or completely unaware about some major things that happened in the past or major ideas out there. I bring all that up to say that if we are to have difficult conversations, we have to give each other space to make mistakes, to learn, to grow. Taking one or two statements from a 3-hour podcast and suggesting that they encapsulate who I am, I was, or ever will be, is a standard that we can't hold each other to. I don't think anyone can live up to that kind of standard. At least I know I can't. The conversation with Yaron is mild relative to some conversations that I will likely have in the coming year. Please continue to challenge me, but please try to do so with love and with patience. I promise to work my ass off to improve. Whether I'm successful at that or not, we shall see. If you enjoy this thing, subscribe on YouTube, review it with 5 stars on Apple Podcasts, follow on Spotify, support on Patreon, or connect with me on Twitter at Lex Fridman. And now, here's my conversation with Andrew Huberman. You've mentioned that in your lab at Stanford, you induce stress by putting people into virtual reality and having them go through one of a set of experiences. I think you mentioned this on Rogan or with Whitney that scare them. So just on a practical, psychological level and maybe on a philosophical level, what are people afraid of? What are the fears? What are these fear experiences that you find to be effective?
Yeah, so it depends on the person, obviously. And we should probably define fear, right? Because you can, without going too far down the rabbit hole of defining these things, you can't really have fear without stress, but you could have stress without fear. And you can't really have trauma without fear and stress, but you could have fear and stress without trauma. So, we can start playing the word game. And that actually is one of the motivations for even having a laboratory that studies these things, is that we really need better physiological, neuroscientific, and operational definitions of what these things are. I mean, the field of understanding emotions and states, which is mainly what I'm interested in, is very complicated. But we can do away with a lot of complicated debate and say, in our laboratory, what we're looking for to assign it a value of fear is a big inflection in autonomic arousal, so increases in heart rate, increases in breathing, perspiration, pupil dilation, all the hallmark signature features of the stress response. Mm-hmm. And in some cases, we have the benefit of getting neurosurgery patients where we've got electrodes in their amygdala and their insula and the orbital frontal cortex down beneath the skull. So these are chronically implanted electrodes. We're getting multi-unit signals, and we can start seeing some central features of meaning within the brain. And what's interesting is that, as trivial as it might seem in listening to it, almost everybody responds to heights and falling from a high virtual place with a very strong stress, if not fear response. And that's because the visual vestibular apparatus, right, the optic flow and how it links to the, balanced semicircular canals of the inner ears, all this technical stuff. But really, all of that pulls all your physiology, the feeling that your stomach is dropping, the feeling that you're sweating, even though you're not afraid of falling off this virtual platform, but you feel as if you're falling, because of the optic flow. That one is universal. So we've got a dive with great white sharks experience where you actually exit the cage. We went out and did this in the real world and brought back 360 video that's built out pretty.
Oh, so this is actual 360 video.
360
That's
video.
awesome.
And this was important to us, right? So when we decided to set up this platform, a lot of the motivation was that a lot of the studies of these things in laboratories, I don't want to call them lame because I want to be respectful of the people that did this stuff before, but they'd study fear by, showing subjects a picture of a bloody arm or a snake or something like that. And it just, unless you have a snake phobia, it just wasn't creating a real enough experience. So we need to do something where people aren't going to get injured, but where we can tap into the physiology and that thing of presence of people momentarily, not the whole time, but momentarily forgetting they're in a laboratory. Mm-hmm. And so heights will always do it. And if people want to challenge me on this, I like to point to that movie Free Solo, which was wild because, it's an incredible movie, but I think a lot of its popularity can be explained by a puzzle, which is you knew he was going to live when you walked in the theater. Right. Or you watched it at home. Yeah. You knew before that he survived, and yet it was still scary that people somehow were able to put themselves into that experience or into Alex's experience enough that they were concerned or worried or afraid at some level. So heights always does it. If we get people who have generalized anxiety, these are people who wake up and move through life at a generally higher state of autonomic arousal and anxiety, then we can tip them a little bit more easily with things that don't necessarily get everyone afraid. Things like claustrophobia, public speaking. That's going to vary from person to person. And then if you're afraid of sharks, like my sister, for instance, is afraid of sharks, she won't even come to my laboratory. Because there's a thing about sharks in it. That's how terrified some people are of these specific stimuli. But heights gets them every time.
Yeah,
and
I'm terrified of heights.
It's when we have you step off a platform, virtual platform, and it's a flat floor in my lab. But you're up there.
Well, you actually allow them the possibility in the virtual world to actually take the leap of faith.
Yeah, maybe I should describe a little bit of the experiment. So. Without giving away too much in case someone wants to be a subject in one of these experiments, we have them playing a cognitive game. It's a simple lights out kind of game where you're pointing a cursor and turning out lights on a grid, but it gets increasingly complex and it speeds up on them. And, there's a failure point for everybody where they just can't make the motor commands fast enough. And then we surprise people essentially by placing them virtually. All of a sudden, they're on a narrow platform between two buildings. Yeah. And then we encourage them, or we cue them by talking to them through a microphone to continue across that platform to continue the game. And some people they just won't. They actually will get down on the ground and hold on to a virtual beam that doesn't even exist on a flat floor. And so what this really tells us is the power of the brain to enter these virtual states as if they were real. And we really think that anchoring the visual and the vestibular, the balance components of the nervous system, are what bring people into that presence so quickly. There's also the potential, and we haven't done this yet, to bring in 360 sound. So the reason we did 360 video is that when we started all this back in 2016, a lot of the VR was pretty lame, frankly. It was CGI. It just wasn't real enough. But with 360 video, we knew that we could get people into this presence where they think they're in a real experience more quickly. And our friend Michael Muller, who I was introduced to because of the project, I reached out to some friends. Michael Muller is a very famous portrait photographer in Hollywood, but he dives with great white sharks and he leaves the cage. And so we worked with him to build a 360 video apparatus that we could swim under water with, went out to Guadalupe Island, Mexico, and actually got the experience. It was a lot of fun. It was there were some interesting moments out there of danger, but it came back with that video and built that for the sharks. And then we realized we need to do this for everything. We need to do it for heights. We need to do it for public speaking, for claustrophobia. And what's missing still is 360 sound, where 360 sound would be, for instance, if I were to turn around and there was a like a giant attack dog there, the moment I would turn around and see it, the dog would growl. But if I turned back toward you,
Right.
then it would be silent. So, and that brings a very real element to one's own behavior, where you don't know what's going to happen if you turn a corner. Whereas if there's a dog growling behind me and I turn around and then I turn back to you and it's still growling,
Yeah.
That might seem like more of an impending threat, but and sustained threat. But actually, it's when you start linking your own body movements to the experience. So when it's closed loop, where my movements and choices are starting to influence things, and they're getting scarier and scarier, that's when you can really drive people's nervous system down these paths of high states of stress and fear. Now, we don't want to traumatize people, obviously, but we also study a number of tools that allow them to calm themselves in these environments. So the short answer is heights.
Heights.
Yeah.
Well, from a psychology and from a neuroscience perspective, this whole construction that you've developed is fascinating. We did this a little bit with autonomous vehicles. So to try to understand the decision-making process of a pedestrian when they cross the road, and trying to create an experience of a car, that can run you over. So there's the danger of there. I was so surprised how real that whole world was. And the graphics that we built wasn't ultra realistic or anything, but I was still afraid of being hit by a car. Everybody we tested were really afraid of being hit by that car.
Even though it was all a simulation.
It was all a simulation. It was kind of boxy, actually. I mean, it wasn't like ultra realistic simulation. And it's fascinating.
Looms and heights. So any kind of depth, we're just programmed to not necessarily recoil, but to be cautious about that edge and that depth. And then looms, things coming at us that are getting larger. There are looming sensing neurons even in the retina at a very, very early stage of visual processing. And incidentally, the way Muller and folks learned how to not get eaten by great white sharks when you're swimming outside the cage is as they start lumbering in, you swim toward them. And they get very confused when you loom on them, because clearly you're smaller. Clearly they could eat you if they wanted to. But there's something about forward movement toward any creature that creature questions whether or not it would be a good idea to generate forward movement toward you. And so that's actually the survival tool of these cage exit white shark divers.
Are you playing around with, like, one of the critical things for the autonomous vehicle research is you couldn't do 360 video because there's a game theoretic, there's an interactive element that's really necessary. So maybe people realize this, maybe they don't, but 360 video, you obviously, well, it's actually not that obvious to people, but you can't change the reality that you're watching.
That's right.
So, but you find that's like, is there something fundamental about fear and stress that the interactive element is essential for? Or do you find you can arouse people with just the video?
Great question. It works best to use mixed reality. So we have a snake stimulus. I personally don't like snakes at all. I don't mind spiders. We also have a spider stimulus, but like snakes, I just don't like them. There's something about the slithering and it creates a visceral response for me. Some people not so much, and they have lower levels of stress and fear in there. But one way that we can get them to feel more of that is to use mixed reality, where we have an actual physical bat and they have to stomp out the snake as opposed to just walk to a little safe corner, which then makes the snake disappear. That tends to be not as stressful as if they have a physical weapon. And so you got people in there, banging on the floor against this thing. And there's something about engaging that makes it more of a threat. Now, I should also mention, we always get the subjective report from the subject of what they experience, because we never want to project our own ideas about what they were feeling. But that's the beauty of working with humans, is you can ask them how they feel.
Exactly.
And humans aren't great at explaining how they feel, but it's a lot easier to understand what they're saying than a mouse or a macaque monkey is saying. So it's the best we can do is language plus these physiological and neurophysiological signals.
Is there something you've learned about yourself, about your deepest fears? Like you said, snakes. Is there something that, like, if I were to torture you, I'm Russian, so, I always kind of think, how can I murder this person that entered the room, but also how can I torture you to get some information out of you? What would I go with?
It's interesting you should say that. I never considered myself claustrophobic, but because I don't mind small environments provided they're well ventilated. But I before COVID, I started going to this Russian banya.
Yeah.
And then which I'm curious. And I had never been to a banya.
Yeah.
So, the whole experience of really, really hot sauna.
Yeah.
And what do they call it? The platza. They're hitting you with the leaves and and it gets really hot and humid in there. And there were a couple times where I thought, okay, this thing is below ground. It's in a city where there are a lot of earthquakes. Like if this place crumbled and we were stuck in here, and I'd start getting a little panicky, and I realized I'm like, I don't like small confined spaces with poor ventilation. So I realized I think I have some claustrophobia, and I wasn't aware of that before. So I put myself into our own claustrophobia stimulus, which involves getting into an elevator and with a bunch of people, virtual people, and the elevator gets stalled. And at first you're fine, you feel fine. But then as we start modulating the environment and we actually can control levels of oxygen in the environment if we want to, it is really uncomfortable for me. And I never would have thought, I fly, I'm comfortable in planes, but it is really uncomfortable. And so I think I've unhatched a bit of a claustrophobia.
Yeah. Yeah, for me as well, probably. That one is pretty bad. The heights, I tried to overcome. So I went to skydiving to try to overcome the fear of heights, but that didn't help.
Did you jump out?
Yeah, jumped out, but it was fundamentally different experience. And I guess there could be a lot of different flavors of fear of heights, maybe, but the one I have didn't seem to be connected to jumping out of a plane. It's a very different, because like once you accept that you're going to jump, then it's a different thing. I think what I'm afraid of is the moments before it is the scariest part.
Absolutely.
And I don't think that's emphasized in the skydiving experience as much, and also just the acceptance of the fact that it's going to happen. So once you accept that it's going to happen, it's not as scary. It's the fact that it's not supposed to happen, and it might. That's the scary part. I guess I'm not being eloquent in this description, but there's something about skydiving that was actually philosophically liberating. I was like, wow, it was the possibility that you can walk on a surface, and then at a certain point there's no surface anymore to walk on, and it's all of a sudden the world becomes 3-dimensional, and there's this freedom of floating, that the concept of Earth disappears for a brief few seconds. I don't know. That was
wild.
That was wild, but I'm still terrified of heights. So, I mean, one thing I want to ask, just on fear, because it's so fascinating, is have you learned anything about what it takes to overcome fears?
Yes, and that comes from a research study standpoint, two parallel tracks of research. One was done actually in mice, because we have a mouse lab also where we can probe around in different brain areas and try and figure out what interesting brain areas we might want to probe around in humans. And a graduate student in my lab, she's now at Caltech, Lindsay Soleil, published a paper back in 2018 showing that what at first might seem a little bit obvious, but the mechanisms are not, which is that there are really 3 responses to fear. You can pause, you can freeze essentially. You can retreat, you can back up, or you can go forward. And there's a single hub of neurons in the midbrain. It's actually not the midbrain, but it's in the middle of the thalamus, which is a forebrain structure. And depending on which neurons are active there's a much higher probability that a mouse, or it turns out, or a human will advance in the face of fear, or will pause, or will retreat. Now, that just assigns a neural structure to a behavioral phenomenon. But what's interesting is that it turns out that the lowest level of stress or autonomic arousal is actually associated with the pausing and freezing response. Mm-hmm. Then as the threat becomes more impending, and we used visual looms in this case, the retreat response has a slightly higher level of autonomic arousal and stress. So think about playing hide and go seek, and you're trying to stay quiet in a closet that you're hiding. if you're very calm, it's easy to stay quiet and still. As your level of stress goes up, it's harder to maintain that level of quiet and stillness. You see this also in animals that are stalking. A cat will chatter its teeth. That's actually sort of top-down inhibition and trying to restrain behavior. So the freeze response is actually an active response, but it's fairly low stress. And what was interesting to us is that the highest level of autonomic arousal was associated with the forward movement toward the threat. So in your case, jumping out of the plane. However, the forward movement in the face of threat was linked to the activation of what we call collateral, which means just a side connection, literally a wire in the brain that connects to the dopamine circuits for reward. And so when one safely and adaptively, meaning you survive, moves through a threat or toward a threat, it's rewarded as a positive experience. And so the key, it actually maps very well to cognitive behavioral therapy and a lot of the existing treatments for trauma, is that you have to confront the thing that makes you afraid. So otherwise you exist in this very low level of reverberatory circuit activity where the circuits for autonomic arousal are humming, and they're humming more and more and more. And we have to remember that stress and fear and threat were designed to agitate us so that we actually move. So the reason I mention this is I think a lot of times people think that the maximum, stress response or fear response is to freeze and to lock up.
Yeah.
But that's actually not the maximum stress response. The maximum stress response is to advance, but it's associated with reward. It has positive valence.
Interesting. Yeah.
So there's this kind of, everyone always thinks about the bell shape, the sort of hump shape curve for, at low levels of arousal, performance is low, and as it increases, performance goes higher, and then it drops off as you get really stressed. But there's another bump further out the distribution where you perform very well under very high levels of stress. And so we've been spending a lot of time in humans and in animals exploring what it takes to get people comfortable to go to that place, and also to let them experience how there are heightened states of cognition there. There's changes in time perception that allow you to evaluate your environment at a faster frame rate, essentially. This is the Matrix, as a lot of people think of it. Yeah. But we tend to think about fear as all the low-level stuff where things aren't worked out. But there are a lot of different features to the fear response. And so we think about it quantitatively, and we think about it from a circuit perspective in terms of outcomes, and we try and weigh that against the threat. So we never want people to put themselves in unnecessary risk, but that's where the VR is fun, because you can push people hard without risk of physically injuring them.
And that's, like you said, the little bump, that seems to be a very small fraction of the human experience, right? So it's kind of fascinating to study it, because most of us move through life without ever experiencing that kind of focus.
Well, everything's in a peak state there. I really think that's where optimal performance lies.
There's so many interesting words here, but what's performance and what's optimal performance? We're talking about mental ability to perceive the environment quickly, to make actions quickly. What's optimal performance?
Yeah, well, it's very subjective, and it varies depending on task and environment. So one way we can make it a little bit more operational and concrete is to say, there is a sweet spot, if you will, where the level of internal autonomic arousal, aka stress or alertness, whatever you want to call it, is ideally matched to the speed of whatever challenge you happen to be facing in the outside world. So we all have perception of the outside world as exteroception, and then perception of our internal real estate, interoception. And when those two things, when interoception and exteroception are matched along a couple dimensions, performance tends to increase, or tends to be in an optimal range. So for instance, I don't play guitar, but I know you play guitar. So let's say you're trying to learn something new on the guitar. I'm not saying that being in these super high states of activation are the best place for you to be in order to learn. It may be that your internal arousal needs to be at a level where your analysis of space and time has to be well matched to the information coming in and what you're trying to do in terms of performance, in terms of playing chords and notes and so forth. Now, in these cases of high threat where things are coming in quickly and animals and humans need to react very quickly, the higher your state of autonomic arousal, the better, because you're slicing time more finely just because of the way the autonomic system works. It, the pupil dilation, for instance, and movement of the lens essentially changes your optics, and that's obvious. But with the change in optics is a change in how you bin time and slice time, which allows you to get more frames per second readout. With the guitar learning, for instance, it might actually be that you want to be almost sleepy, almost in a kind of drowsy state to be able to, and I don't play music, so I can't, I'm guessing here, but sense some of the nuance in the chords or the ways that you're to be relaxed enough that your fingers can follow an external cue. So matching the movement of your fingers to something that's pure exteroception. And so there is no perfect autonomic state for performance. This is why I don't favor terms like flow, because they're not well operationally defined enough. But I do believe that optimal or peak performance is going to arise when internal state is ideally matched to the space-time features of the external demands.
So there's some slicing of time that happens, and then you're able to adjust, so slice time more finely or less finely in order to adjust to the stimulus, the dynamics of the stimulus. What about the realm of ideas? So like, I'm a big believer. There's a guy named Cal Newport who wrote a book about deep work.
Oh yeah, I love that book. Yeah,
he's great. So one of the nice things, I've always practiced deep work, but it's always nice to have words put to the concepts that you've practiced. It somehow makes them more concrete and allows you to get better. It turns it into a skill that you can get better at. But I also value deep thinking, where you think, it's almost meditative. You think about a particular concept for long periods of time. The programming, you have to do that kind of thing for. You just have to hold this concept, like you hold it, and then you take steps with it. You take further steps, and you're holding relatively complicated things in your mind as you're thinking about them. And there's a lot of, the hardest part is there's frustrating things like you take a step and it turns out to be the wrong direction, so you have to calmly turn around and take a step back, and then you're kind of like exploring through the space of ideas. Is there something about your study of optimal performance that could be applied to the act of thinking as opposed to action?
Well, we haven't done too much work there, but but I think I can comment on it from a neuroscience perspective, which is really all I do is, we do experiments in the lab, but looking at things through the lens of neuroscience. So what you're describing can be mapped fairly well to working memory, just keeping things online and updating them as they change and information is coming back into your brain. Jack Feldman, who I'm a huge fan of and fortunate to be friends with, is a professor at UCLA, works on respiration and breathing, but he has a physics background. And so he thinks about respiration and breathing in terms of ground states and how they modulate other states. Very, very interesting and I think important work. Jack has an answer to your question. So I'm not going to get this exactly right because this is lifted from a coffee conversation that we had about a month ago. But apologies in advance but I think I can get mostly right. So we were talking about this, about how the brain updates cognitive states depending on demands and thinking in particular. And he used an interesting example. I'd be curious to know if you agree or disagree. He said, most great mathematics is done by people in their late teens and 20s, and even you could say early 20s, sometimes into the late 20s, but not much further on. Yeah. Maybe I just insulted some mathematicians.
No, that's true.
And I think that it demands, his argument was there's a tremendous demand on working memory to work out theorems in math and to keep a number of plates spinning, so to speak, mentally and run back and forth between them, updating them. In physics, Jack said, and I think this makes sense to me too, that there's a reliance on working memory, but an increased reliance on some sort of deep deep memory and deep memory stores probably stuff that's moved out of the hippocampus and forebrain and into the cortex, and is more some episodic and declarative stuff, but really, so you're pulling from your library, basically. It's not all RAM, it's not all working memory. And then in biology, and physicists tend to have very active careers into their 30s and 40s and 50s and so forth, sometimes later. And then in biology, you see careers that have a much longer arc, kind of these protracted careers, often people still in their 60s and 70s doing really terrific work. Not always doing it with their own hands, because the people in the labs are doing them, of course, but and that work does tend to rely on insights gained from having a very deep knowledge base, where you can remember a paper or maybe a figure in a paper. You could go look it up if you wanted to, but it's very different than the working memory of the mathematician. And so when you're talking about coding or being in that tunnel of thought and trying to iterate and keeping a lot of plates spinning, it speaks directly to working memory. My lab hasn't done too much of that.
With working memory?
But we are pushing working memory when we have people do things like these simple lights out tasks while they're under. We can increase the cognitive load by increasing the level of autonomic arousal to the point where they start doing less well.
Yeah.
And, everyone has a cliff. This is what's kind of fun. We've had, SEAL team operators come to the lab. We've had people from other units in the military. We've had a range of intellects and backgrounds and all sorts of things. And everyone has a cliff. And those cliffs sometimes show up as a function of the demands of speed of processing, or how many things you need to keep online. I mean, we're all limited at some point in the number of things we can keep online. So what you're describing is very interesting, because I think it has to do with how narrow or broad the information set is. And I'm not an active programmer, so this is a regime I don't really fully know, so I don't want to comment about it in any way that doesn't suggest that. But I think that what you're talking about is top-down control. So this is prefrontal cortex keeping every bit of reflexive circuitry at bay. The one that makes you want to get up and use the restroom, the one that makes you want to check your phone, all of that, but also running these anterior thalamus to prefrontal cortex loops, which we know are very important for working memory.
Yeah, let me try to think through this a little bit. So reducing the process of thinking to working memory access is tricky. He's probably ultimately correct. But if I were to say some of the most challenging things that an engineer has to do, and a scientific thinker, I would say it's kind of depressing to think that we do that best in our 20s, but is this kind of first principles thinking step of saying you're accessing the things that you know, and then saying, well, how do I do this differently than I've done it before? This weird, like, stepping back, like, is this right? Let's try it this other way. That's the most mentally taxing step. It's like you've gotten quite good at this particular pattern of how you solve this particular problem. So there's a pattern recognition first. You're like, okay, I know how to build a thing that solves this particular problem in programming, say. And then the question is, but can I do it much better? And I don't know what the hell that is. I don't know if that's accessing working memory. That's almost maybe it is accessing memory in a sense. It's trying to find similar patterns in a totally different place that could be projected onto this. But you're not querying facts. You're querying like functional things, like
it's patterns. I mean, you're running out. You're testing algorithms.
Yeah,
right. You're testing algorithms.
Yes.
So I want to just because I know some of the people listening to this, and you have basis in scientific training and have scientific training. So I want to be clear. I think we can be correct about some things, like the role of working memory in these kinds of processes, without being exhaustive. We're not saying they're the only thing. We're not, we can be correct, but not assume that that's the only thing involved, right? And I mean, neuroscience, let's face it, is still in its infancy. I mean, we probably know 1% of what there is to know about the brain. we've learned so much, and yet there may be global states that underlie this that make prefrontal circuitry work differently than it would in a different regime or even time of day. I mean, there's a lot of mysteries about this, but so I just want to make sure that we sort of we're aiming for precision and accuracy, but we're not going to be exhaustive.
Yeah.
So there's a difference there, and I think sometimes in the vastness of the internet that gets forgotten. So the other is that we think about we think about these operations at really focused, keeping a lot of things online. But what you were describing is actually it speaks to the very real possibility, probably that with certainty, there's another element to all this, which is when you're trying out lots of things, in particular, lots of different algorithms, you don't want to be in a state of very high autonomic arousal. That's not what you want, because the higher level of autonomic arousal and stress in the system, the more rigidly you're going to analyze space and time.
Right.
And what you're talking about is playing with space-time dimensionality. And I want to be very clear. I mean, I'm the son of a physicist. I am not a physicist. When I talk about space and time, I'm literally talking about visual space and how long it takes for my finger to move from this point to this point.
You are facing a tiger and trying to figure out how to avoid being eaten by the tiger.
And that's primarily going to be determined by the visual system in humans. Yeah. We don't walk through space, for instance, like a scent hound would, and look at three-dimensional scent plumes. When a scent hound goes out in the environment, they have depth to their the odor trails they're following. And they don't think about them. We don't think about odor trails. You might say, oh, well, the smell's getting more intense. Aha. Yeah. But they actually have three-dimensional odor trails. So they see a cone of odor. See, of course, with their nose, with their olfactory cortex. We do that with our visual system, and we parse time, often subconsciously, mainly with our visual system, also with our auditory system. And this shows up for the musicians out there. Metronomes are a great way to play with this. Bass drumming, when the frequency of bass drumming changes, your perception of time changes quite a lot. So in any event, space and time are linked through the sensory apparatus, through the eyes and ears and nose, and probably through taste too, and through touch for us, but mainly through vision. So when you drop into some coding or iterating through a creative process or trying to solve something hard, you can't really do that well if you're in a rigid, high level of autonomic arousal, because you're plugging in algorithms that are in this space regime, this time regime matches. It's space-time matched. Whereas creativity, I always think the lava lamp is actually a pretty good example, even though it has these counterculture, new agey connotations, because you actually don't know which direction things are going to change. And so in drowsy states, sleeping and drowsy states, space and time become dislodged from one another somewhat, and they're very fluid. And I think that's why a lot of solutions come to people after sleep and naps. And this could even take us into a discussion, if you like, about psychedelics. And what we now know, for instance, that people thought that psychedelics work by just creating spontaneous bursting of neurons and hallucinations. But the 5H2C and 2C and 2A receptors, which are the main sites for things like LSD and psilocybin and some of the other the ones that create hallucinations, the drugs that create hallucinations, most of those receptors are actually in the collection of neurons that encase the thalamus, which is where all the sensory information goes into, a structure called the thalamic reticular nucleus. And it's an inhibitory structure that makes sure that when we're sitting here talking, that I'm mainly focused on whatever I'm seeing visually, that I'm essentially eliminating a lot of sensory information. Under conditions where people take psychedelics and these particular serotonin receptors are activated, that inhibitory shell, it's literally shaped like a shell, starts losing its ability to inhibit the passage of sensory information. But mostly the effects of psychedelics are because the lateral connectivity in layer 5 of cortex across cortical areas is increased. And what that does is that means that the space-time relationship for vision, like moving my finger from here to here, very rigid space-time relationship, right? If I slow it down, it's slower, obviously, but there's a prediction that can be made based on the neurons in the retina and the cortex. On psychedelics, this could be a very strange experience.
Yeah.
But the auditory system has one that's slightly different. space-time, and they're matched to one another in deeper circuits in the brain. The olfactory system has a different space-time relationship to it. So under conditions of these increased activation of these serotonin receptors, space and time across sensory areas starts being fluid. So I'm no longer running the algorithm for moving my finger from here to here and making a prediction based on vision alone. This is where people talk about hearing sights, right? You start linking this might actually make a sound in a psychedelic state. Now, I'm not suggesting people run out and do psychedelics because it's very disorganized, but essentially what you're doing is you're mixing the algorithms. And so when you talk about being able to access new solutions, you don't need to rely on psychedelics. If people choose to do that, that's their business. But in drowsy states, this lateral connectivity is increased as well. The shell of the thalamus shuts down. And these are through these so-called pons geniculate occipital waves. And what's happening is you're getting whole brain activation at a level that you start mixing algorithms. And so sometimes I think solutions come not from being in that narrow tunnel of space-time and strong activation of working memory and trying to, iterate if this, then this, very strong deductive and inductive thinking, and working from first principles, but also from states where something that was an algorithm that you never had in existence before suddenly gets lumped with another algorithm. And all of a sudden, a new possibility comes to mind. And so space and time need to be fluid, and space and time need to be rigid in order to come up with something meaningful. And I realize I'm riffing long on this, but this is why I think, there was so much interest a few years ago with Michael Pollan's book and other things happening about psychedelics as a pathway to exploration and all this kind of thing. But the real question is what you export back from those experiences.
Right.
Because dreams are amazing, but if you can't bring anything back from them, they're just amazing.
I wonder how to experiment with the mind without any medical assistance first. Like, I pushed my mind in all kinds of directions. I definitely want to, I did shrooms a couple of times. I definitely want to figure out how I can experiment with psychedelics. I'm talking to Rick Doblin, I think. Doblin. Soon. I went back and forth. So he does all these studies on psychedelics. And he keeps ignoring the parts of my email that asks, like, how do I participate in these studies?
Yeah, well, there are some legality issues. I mean, conversation, I want to be very clear. I'm not saying that anyone should run out and do psychedelics. I think that drowsy states and sleep states are super interesting for accessing some of these more creative states of mind. Hypnosis is something that my colleague David Spiegel, Associate Chair of Psychiatry at Stanford, works on, where also, again, it's a unique state because you have narrow context. So this is very kind of tunnel vision and yet deeply relaxed, where new algorithms, if you will, can start to surface. Strong state for inducing neuroplasticity. And I think that, so if I had I'm part of a group that it's called the Liminal Collective, as a group of people that get together and talk about just wild ideas, but they try and implement. And it's a really interesting group. Some people from military, from Logitech, and some other backgrounds, academic backgrounds. And I was asked, what would be, if you could create a tool, if you just had a tool like your magic wand wish for the day, what would it be? I thought it would be really interesting if someone could develop psychedelics that have on-off switches. So you could go into a psychedelic state very deeply for 10 minutes, but you could launch yourself out of that state and place yourself into a linear real world state very quickly, so that you could extract whatever it was that happened in that experience and then go back in if you wanted. Because the problem with psychedelic states and dream states is that, first of all, a lot of the reason people do them is they're lying. They say they want plasticity and they want all this stuff. They want a peak experience inside of an amplified experience. So they're kind of seeking something unusual. And I think we should just be honest about that, because a lot of times they're not trying to make their brain better. They're just trying to experience something really amazing. But the problem is space and time are so unlocked in these states, just like they are in dreams, that you can really end up with a whole lot of nothing. You can have an amazing amplified experience housed in an amplified experience and come out of that thinking you had a meaningful experience when you didn't bring anything back.
You didn't bring anything back. All you have is a fuzzy memory of having a transformational experience,
Right.
but you don't
You could
actually
be-
have tools to bring back,
That's
or I
right.
just sorry, actually concrete ideas to bring back. Yeah, it's interesting. You should, yeah, I wonder if it's possible to do that with the mind to be able to hop back and forth.
Well, I think that's where the real power of, adjusting states is going to be. It probably will be with devices. I mean, maybe it'll be done through pharmacology. It's just that it's hard to do on-off switches in human pharmacology. That we have them for animals. I mean, we have Cre-flip recombinases, and we have channel opsins and halorhodopsins and all these kinds of things. But to do that work in humans is tricky. But I think you could do it with virtual reality, augmented reality, and other devices that bring more of the somatic experience into it.
You're, of course, a scientist who's studying humans as a collective. I tend to be just a one-person scientist of just looking at myself. And, I play, when these deep thinking, deep work sessions, I'm very cognizant, like in the morning, that there's times when my mind is so like eloquent at being able to jump around from ideas and hold them all together. And I'm almost like I step back from a third person perspective and enjoy that, whatever that mind is doing. I do not waste those moments. And I'm very conscious of this like little creature that woke up, that's only awake for, if we're being honest, maybe a couple hours a day.
Early part of the day for you.
Early part of the day, not always. Well, early part of the day for me is a very fluid concept. So
you're one of those.
Yeah, I'm one.
Yeah, you're one of those.
Being single, one of the problems, single and no meetings. I don't schedule any meetings. I've been living at like a 28-hour day, so it drifts. So it's all over the place. But after a traditionally defined full night's sleep, whatever the heck that means, I find that like in those moments, there's a clarity of mind that's just this. Everything is effortless, and it's the deepest dives intellectually that I make, and I'm cognizant of it, and I try to bring that to the other parts of the day that don't have it, and treasure them even more in those moments because they only last like 5 or 10 minutes. Because of course, in those moments, you want to do all kinds of stupid stuff that are completely is worthless, like check social media or something like that. But those are the most precious things in intellectual life, is those mental moments of clarity. And I wonder, I'm learning how to control them. I think caffeine is somehow involved. I'm not sure exactly.
Sure. Well, because if you learn how to titrate caffeine, and everyone's slightly different with this, what they need. But if you learn to titrate caffeine with time of day and the kind of work that you're trying to do, you can bring that autonomic arousal state into the close to perfect place.
Yeah.
And then you can tune it in with, sometimes people want a little bit of background music, sometimes they want less, these kinds of things. The early part of the day is interesting because the one thing that's not often discussed is the transition out of sleep. So there's a book, I think it's called Winston Churchill's Nap, and it's about naps and the transition between wake and sleep as a valuable period. I've a long time ago, someone who I respect a lot was mentoring me, said, be very careful about bringing in someone else's sensory experience early in the day. So when I wake up, I'm very drowsy. I sleep well, but I don't emerge from that very quickly. I need a lot of caffeine to wake up and whatnot. But there's this concept of getting the download from sleep, which is, in sleep, you were essentially expunging the things that you don't need, the stuff that was meaningless from the previous day. But you were also running variations on these algorithms of whatever it is you're trying to work out in life on short time scales like the previous day and long time scales like your whole life. And those lateral connections in layer 5 of the neocortex are very robustly active and across sensory areas, and you're running an algorithm or a brain. It's a brain state that would be useless in waking. You wouldn't get anything done. You'd be the person talking to yourself in the hallway or something about something that no one else can see. But in those states, you do the theory is that you arrive at certain solutions, and those solutions will reveal themselves in the early part of the day, unless you interfere with them by bringing in social media is a good example of you immediately enter somebody else's space-time sensory relationship. Someone is the conductor of your thoughts in that case. And so many people have written about this. What I'm saying isn't entirely new, but allowing the download to occur in the early part of the day and asking the question, am I more in my head or external? Am I in more of an interoceptive or exteroceptive mode? And depending on the kind of work you need to do, if it sounds like for you, it's very interoceptive you've got a lot of thinking going on and a lot of computing going on, allowing yourself to transition out of that sleep state and arrive with those solutions from sleep and plug into the work really deeply.
Oh, yeah.
And only then allowing things like music, news, social media. Doesn't mean you shouldn't talk to loved ones and see faces and things like that. But some people have taken this to the extreme. When I was a graduate student at Berkeley, there was a guy, there was a professor, brilliant, odd, but brilliant, who was so fixated on this concept that he wouldn't look at faces in the early part of the day because he just didn't want anything else to impact him. Now, he didn't have the most rounded life, I suppose. But if you're talking about cognitive performance, this could actually be very beneficial.
You said so many brilliant things. So one, if you read books that describe the habits of brilliant people, like writers, they do control that sensory experience in the hours after wake. Like many writers, they have a particular habit of several hours early in the morning of actual writing. They don't do anything else for the rest of the day, but they're very sensitive to noises and so on. I think they make it very difficult to live with them. I'm definitely like that. Like I love to control the sensory, how much information is coming in. There's something about the peaceful, just everything being peaceful. At the same time, and we're talking to a mutual friend of Whitney Cummings, who has a mansion, a castle on top of a cliff in the middle of nowhere. She actually purchased her own island. So she wants silence. She wants to control how much sound is coming in.
She's very sensitive to sound and environment.
Yeah.
Beautiful home and environment, but like clearly puts a lot of attention into details. Yeah, and very creative.
Yeah, and that allows her creativity to flourish. I don't like that. Feels like a slippery slope. So I enjoy introducing noises and signals and training my mind to be able to tune them out, because I feel like you can't always control the environment so perfectly, because your mind gets comfortable with that. I think it's a skill that you want to learn to be able to shut it off. Like I often go to, back before COVID, to a coffee shop. It really annoys me when there's sounds and voices and so on, but I feel like I can train my mind to block them out. So it's a balance, I think.
Yeah, and I think two things come to mind as you're saying this. First of all, we're talking about what's best for work is not always what's best for completeness of life. I mean, autism is probably many things. Like when you hit autism, just like there are probably 50 ways to get a fever. There are probably 50 ways that the brain can create what looks like autism, or what people call autism. But there's an interesting set of studies that have come out of David Ginty's lab at Harvard Med, looking at, these are mouse mutants where these are models for autism where nothing is disrupted in the brain proper and in the central nervous system, but the sensory neurons, the ones that innervate the skin and the ears and everything, are hypersensitive, and this maps to a mutation in certain forms of human autism. So this means that the overload of sensory information and sensory experience that a lot of autistics feel, that they can't tolerate things, and then they get the stereotype behaviors, the rocking and the kind of the shouting. We always thought of that as a brain problem. In some cases it might be, but in many cases it's because they just can't, they seem to have it's like turning the volume up on every sense. And so they're overwhelmed. And none of us want to become like that. I think it's very hard for them, and it's hard for their parents and so forth. So I like the coffee shop example, because the way I think about trying to build up resilience, physically or mentally or otherwise, is one of, I guess we could call it, I like to call it limbic friction. That's not a real scientific term, and I acknowledge that. I'm making it up now because I think it captures the concept, which is that, we always hear about resilience. It makes it sound like, under stress where everything's coming at you, you're going to stay calm. But there's another, so the limbic system wants to pull you in some direction, typically in the direction of reflexive behavior. And the prefrontal cortex, through top-down mechanisms, has to suppress that and say, no, we're not going to respond to the banging of the coffee cups behind me, or I'm going to keep focusing. That's pure top-down control. So limbic friction is high in that environment. You've put yourself into a high limbic friction environment, meaning that the prefrontal cortex has to work really hard. But there's another side to limbic friction too, which is when you're very sleepy, there's nothing incoming. It can be completely silent. And it's hard to engage and focus because you're drifting off and you're getting sleepy. So their limbic friction is high, but for the opposite reason, autonomic arousal is too low. So they're turning on Netflix in the background or looping a song might boost your level of alertness that will allow top-down control to be in exactly the sweet spot you want it. So this is why earlier I was saying it's all about how we feel inside relative to what's going on the outside. We're constantly in this. I guess one way you could envision it spatially, especially if people are listening to this just on audio, is I like to think about it kind of like a glass barbell, where one sphere of perception and attention can be on what's going on with me, and one sphere of attention can be on what's going on with you or something else in the room or in my environment. But this barbell isn't rigid. It's not really glass. Mm-hmm. Would plasma work here? I don't know anything about plasma. Sorry, I don't know.
Yeah.
Okay. But so imagine that this thing can contort. The size of the globes at the end of this barbell can get bigger or smaller. So let's say I close my eyes and I bring all my experience into what's going on through interoception internally. Now it's as if I've got two orbs of perception just on my internal state. But I can also do the opposite and bring both orbs of perception outside me. I'm not thinking about my heart rate or my breathing. I'm just thinking about something I see. And what you'll start to realize as you kind of use this spatial model is that two things. One is that it's very dynamic, and that the more relaxed we are, the more these two orbs of attention, the two ends of the barbell, can move around freely. The more alert we are, the more rigid they're going to be tethered in place. Mm-hmm. And that was designed so that if I have a threat in my environment, it's tethered to that threat. Mm-hmm. I'm not going to be, if something's coming to attack me, I'm not going to be like, oh, my breathing cadence is a little bit quick. Yeah. That's not how it works. Why? Because both orbs are linked to that threat. And so my behavior is now actually being driven by something external, even though I think it's internal. And so I don't want to get too abstract here because I'm a neuroscientist, I'm not a theorist. But when you start thinking about models of how the brain works, there are only really three things that neurons do. They're either sensory neurons, they're motor neurons, or they're modulating things. And the models of attention and perception that we have now, 2020, tell us that we've got interoception and exteroception. They're strongly modulated by levels of autonomic arousal. And that if we want to form the optimal relationship to some task or some pressure or something, whether or not it's sleep, an impending threat, or coding, we need to adjust our internal space-time relationship with the external space-time relationship. And I realize I'm repeating what I said earlier, but we can actually assign circuitry to this stuff. It mostly has to do with how much limbic friction there is, how much you're being pulled to some source. That source could be internal. If I have pain, physical pain in my body, I'm going to be much more interoceptive than I am exteroceptive. You could be talking to me and I'm just going to be thinking about that pain. It's very hard. And the other thing that we can link it to is top-down control, meaning anything in our environment that has a lot of salience will tend to bring us into more exteroception than interoception. And again, I don't want to litter the conversation with just a bunch of terms, but what I think it can be useful for people is to do what essentially you've done, Lex, is to start developing an awareness. When I wake up, am I mostly in a mode of interoception or exteroception? When I work well, what does working well look like from the perspective of autonomic arousal? How alert or calm am I? What kind of balance between internal focus and external focus is there? And to sort of watch this process throughout the day.
Can you linger just briefly on, because you use this term a lot, and it'd be nice to try to get a little more color to it, which is interoception and exteroception. What are we exactly talking about? So like, what's included in each category and how much overlap is there?
Interoception would be an awareness of anything that's within the confines or on the surface of my skin. that I'm sensing.
Oh, so literally physiological.
Physiologically, like within the boundaries of my skin, and probably touch to the skin as well. Exteroception would be perception of anything that's beyond the reach of my skin. So that bottle of water, a scent, a sound. Although, and this can change dramatically, actually. If you have headphones in, you tend to hear things in your head as opposed to a speaker in the room.
Yeah.
This is actually the basis of ventriloquism. So there are beautiful experiments done by Greg Reckenzone up at UC Davis, looking at how auditory and visual cues are matched, and you have an array of speakers, and you can, this will become obvious as I say it, but obviously the ventriloquist doesn't throw their voice. Right. What they do is they direct your vision to a particular location, and you think the sound is coming from that location. Yeah. And there are beautiful experiments that Greg and his colleagues have done where they suddenly introduce an auditory visual mismatch, and it freaks people out because you can actually make it seem, from a perception standpoint, as if the sound arrived from the corner of the room and hit you, like physically, and people will recoil. And so sounds aren't getting thrown across the room. They're still coming from a defined location, an array of speakers. But this is the way the brain creates these internal representations. And again, I don't want to go down a rabbit hole, but I think as much as I'm sure the listeners appreciate this, but everything in the brain is an abstraction, right? I mean, they're the sensory apparati there, the eyes and ears and nose and skin and taste and all that are taking information, and with interoception, it's taking information from sensors inside the body, the enteric nervous system for the gut. I've got sensory neurons that innervate my liver, et cetera. Taking all that, and the brain is abstracting that in the same way that if I took a picture of your face and I handed it to you and I'd say, that's you, you'd say, yeah, that's me. But if I were an abstract artist, I'd be doing a little bit more of what the brain does, where if I took a pad and paper, maybe I could do this because I'm a terrible artist, and I could just mix it up, and let's say I would make your eyes like water bottles, but I'd flip them upside down, and I'd start assigning fruits and objects to the different features of your face. And I show it to you, I say, Lex, that's you. You'd say, well, that's not me. And I'd say, no, but that's my abstraction of you. But that's what the brain does. The space-time relationship of the neurons that fire, that encode your face, have no resemblance to your face.
Right.
And I think people don't really, I don't know if people have fully internalized that, but the day that and I'm not sure I fully internalized that because it's weird to think about, but all neurons can do is fire in space and in time, different neurons in different sequences, perhaps with different intensities. Yeah. It's not clear the action potential is all or none, although neuroscientists don't like to talk about that, even though it's been published in Nature a couple times. The action potential for a given neuron doesn't always have the exact same waveform. It's in all the textbooks, but you can modify that waveform.
Well, there's a lot of fascinating stuff with neuroscience about the fuzziness of all the transfer of information from neuron to neuron. I mean, we certainly touch upon it every time we at all try to think about the difference between artificial neural networks and biological neural networks. But can we maybe linger a little bit on this on the circuitry that you're getting at? So the brain is just a bunch of stuff firing, and it forms abstractions that are fascinating and beautiful, like layers upon layers upon layers of abstraction. And I think it, just like when you're programming, I'm programming in Python, it's awe-inspiring to think that underneath it all, it ends up being zeros and ones. And the computer doesn't know about stupid Python or Windows or Linux. It only knows about the zeros and ones. In the same way with the brain, is there something interesting to you or fundamental to you about the circuitry of the brain that allows for the magic that's in our mind to emerge? How much do we understand? I mean, maybe even focusing on the vision system. Is there something specific about the structure of the vision system, the circuitry of it, that allows for the complexity of the vision system to emerge? Or is it all just a complete chaotic mess that we don't understand?
It's definitely not all a chaotic mess that we don't understand if we're talking about vision. And that's not just because I'm a vision scientist.
Let's stick to vision.
Let's stick to vision. Well, because in the beauty of the visual system, the reason David Hubel and Torsten Wiesel won the Nobel Prize was because they were brilliant and forward thinking and adventurous and all that good stuff. But the reason that the visual system is such a great model for addressing these kinds of questions and other systems are hard is we can control the stimuli. We can adjust spatial frequency, how fine the gratings are, thick gratings, thin gratings. We can adjust temporal frequency, how fast things are moving. We can use cone isolating stimuli. We can use, there's so many things that you can do in a controlled way. Whereas if we were talking about cognitive encoding,
Right.
like encoding the space of concepts or something,
Right.
I like you, if I may, am drawn to the big questions
Yes.
in neuroscience. But I confess, in part because of some good advice I got early in my career, and in part because I'm not perhaps smart enough to go after the really high level stuff, I also like to address things that are tractable. And I want, we need to address what we can stand to make some ground on at a given time.
That you can construct brilliant controlled experiments just to study, to really literally answer questions about.
Yeah. I mean, I'm happy to have a talk about consciousness, but it's a scary talk. And I think most people don't want to hear what I have to say, which is, we can save that for later, perhaps. Or
it's an interesting question of, we talk about psychedelics, we can talk about consciousness, we can talk about cognition. Can experiments in neuroscience be constructed to shed any kind of light on these questions? So, I mean, it's cool that vision, to me, vision is probably one of the most beautiful things about human beings. Also, from the AI side, computer vision is some of the most exciting applications of neural networks is in computer vision. But it feels like that's a neighbor of cognition and consciousness. It's just that we maybe haven't come up with experiments to study those yet.
Yeah, the visual system is amazing. We're mostly visual animals to navigate, survive. Humans mainly rely on vision, not smell or something else. But it's a filter for cognition, and it's a strong driver of cognition. Maybe just because it came up, and then we're moving to higher level concepts. Just the way the visual system works can be summarized in a few relatively succinct statements, unlike most of what I've said, which has not been succinct at all.
Let's go there.
The retina.
What's involved?
Yeah, so the retina is this 3 layers of neuron structure at the back of your eye. It's about as thick as a credit card. It is a piece of your brain, and sometimes people think I'm kind of wriggling out of reality by saying that. It's absolutely a piece of the brain. It's a forebrain structure that in the first trimester there's a genetic program that made sure that neural retina, which is part of your central nervous system, was squeezed out into what's called the embryonic eye cups, and that the bone formed with a little hole where the optic nerve is going to connect it to the rest of the brain. And that window into the world is the only window into the world for a mammal, which has a thick skull. Birds have a thin skull, so their pineal gland sits, and lizards too, and snakes actually have a hole so that light can make it down into the pineal directly and entrain melatonin rhythms for time of day and time of year. Humans have to do all that through the eyes. So 3 layers of neurons that are a piece of your brain, they are central nervous system, and the optic nerve connects to the rest of the brain. The neurons in the eye, some just care about luminance, just how bright or dim it is. And they inform the brain about time of day. And then the central circadian clock informs every cell in your body about time of day and make sure that all sorts of good stuff happens if you're getting light in your eyes at the right times. And all sorts of bad things happen if you are getting light randomly throughout the 24-hour cycle. We could talk about all that, but this is a good incentive for keeping a relatively normal schedule, consistent schedule of light exposure. Consistent schedule. Okay. Try and keep a consistent schedule. When you're young, it's easy to go off schedule and recover. As you get older, it gets harder. But you see everything from outcomes in cancer patients to diabetes, improves when people are getting light at a particular time of day and getting darkness at a particular phase of the 24-hour cycle. We were designed to get light and dark at different times of the circadian cycle. That's all that information is coming in through specialized type of neuron in the retina called the melanops, an intrinsically photosensitive ganglion cell discovered by David Burson at Brown University. that's not spatial information. It's subconscious. You don't think, oh, it's daytime. Even if you're looking at the sun, it doesn't matter. It's a photon counter. It's literally counting photons. And it's saying, oh, even though it's a cloudy day, lots of photons coming in. It's winter in Boston. It must be winter. And your system is a little depressed. It's spring. You feel alert. That's not a coincidence. That's these melanopsin cells signaling the circadian clock. There are a bunch of other neurons in the eye that signal to the brain, and they mainly signal the presence of things that are lighter than background or darker than background. So a black object would be darker than background, a light object lighter than background, and that all it's mainly it's looking at pixels mainly. They look at circles, and those neurons have receptive fields, which not everyone will understand, but those neurons respond best to little circles of dark light or little circles of bright light, little circles of red light versus little circles of green light or blue light. And so it sounds very basic. It's like red, green, blue, and circles brighter or dimmer than what's next to it. But that's basically the only information that's sent down the optic nerve. And when we say information, we can be very precise. I don't mean little bits of red traveling down the optic nerve. I mean spikes, neural action potentials in space and time, which for you is like makes total sense. But I think for a lot of people, it's actually beautiful to think about. All that information in the outside world is converted into a language that's very simple. It's just like a few syllables, if you will. And those syllables are being shouted down the optic nerve, converted into a totally different language, like Morse code. Beep, 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 beep. Goes into the brain, and then the thalamus essentially responds in the same way that the retina does. Except the thalamus is also weighting things. It's saying, you know what? That thing was moving faster than everything else, or it's brighter than everything else. So that signal I'm going to allow up to cortex. Or that signal is much redder than it is green, so I'm going to let that signal go through. That signal is much, it's kind of more like the red next to it. Throw that out. The information just doesn't get up into your cortex. And then in cortex, of course, is where perceptions happen. And in V1, if you will, visual area 1, but also some neighboring areas, you start getting representations of things like oriented lines. So there's a neuron that responds to this angle of my hand versus vertical, right? This is the defining work of Huberman Wiesel's Nobel. And it's a very systematic map of orientation, line orientation, direction of movement, and so forth. And that's pretty much, and color. And that's how the visual system is organized all the way up to the cortex. So it's hierarchical. You don't build, I want to be clear, it's hierarchical because you don't build up that line by suddenly having a neuron that responds to lines in some random way. It responds to lines by taking all the dots that are aligned in a vertical stack, and they all converge on one neuron, and then that neuron responds to vertical lines. So it's not random. There's no abstraction at that point, in fact. In fact, if I showed you a black line, I could be sure that if I were imaging V1, that I would see a representation of that black line as a vertical line somewhere in your cortex. So at that point, it's absolutely concrete. It's not abstract. But then things get really mysterious. Some of that information travels further up into the cortex and goes from one visual area to the next, to the next, to the next. So that by the time you get into an area that Nancy Kanwisher at MIT has studied much of her career, the fusiform face area, you start finding single neurons that respond only to your father's face or to Joe Rogan's face, regardless of the orientation of his face. I'm sure if you saw Joe, because you know him well, from across the room and you just saw his profile, you'd be like, oh, that's Joe. Walk over and say hello. The orientation of his face isn't there. You wouldn't even see his eyes necessarily, but he's represented in some abstract way by a neuron that actually would be called the Joe Rogan neuron or collection of neurons.
It might have limits, like I might not recognize him if he was upside down or something like that. It'd be fascinating to see what the limits of that Joe Rogan concept is.
So Nancy's lab has done that because early on she was challenged by people that said there aren't face neurons.
Right.
There are neurons that they only respond to space and time, shapes and things like that, moving in particular directions and orientations. And it turns out Nancy was right. They use these stimuli called Greeble stimuli, which any computer programmer would appreciate, which kind of morphs a face into something gradually that eventually just looks like this like alien thing they call the Greeble. And the neurons don't respond to Greebles in most cases, they only respond to faces and familiar faces. Anyway, I'm summarizing a lot of literature, and forgive me, Nancy, and for those of the Greeble people, if there are anything like, you don't come after me with pitchforks. If you actually, you know what? Come after me with pitchforks. I think you know what I'm trying to do here.
Yeah.
So the point is that in the visual system, it's very concrete up until about visual area 4, which has color pinwheels and seems to respond to pinwheels of colors. And so the stimuli become more and more elaborate. But at some point, you depart that concrete representation and you start getting abstract representations that can't be explained by simple point-to-point wiring. And to take a leap out of the visual system to the higher level concepts, what we talked about in the visual system maps to the auditory system, where you're encoding what? Frequency of tone, sweeps. So this is going to sound weird to do, but like a Doppler, like hearing something, a car passing by, for instance. But at some point, you get into motifs of music that can't be mapped to just a what they call a tonotopic map of frequency. You start abstracting. And if you start thinking about concepts of creativity and love and memory, like what is the map of memory space?
Right.
Well, your memories are very different than mine, but presumably there's enough structure at the early stages of memory processing, or at the early stages of emotional processing, or at the earlier stages of creative processing, that you have the building blocks, your zeros and ones, if you will, but you depart from that eventually. Now, the exception to this, and I want to be really clear, because I was just mainly talking about neocortex, the 6-layered structure on the outside of the brain that explains a lot of human abilities, other animals have them too, is that subcortical structures are a lot more like machines. It's more plug and chug. And what I'm talking about is the machinery that controls heart rate and breathing and receptive fields, neurons that respond to things like temperature on the top of my left hand. And one of the, I came into neuroscience from more of a perspective initially of psychology, but one of the reasons I forced upon myself to learn some electrophysiology, not a ton, but enough, and some molecular biology and about circuitry, is that one of the most beautiful experiences you can have in life, I'm convinced, is to lower an electrode into the cortex and to show a person or an animal, you do this ethically, of course, stimulus, like an oriented line or a face. And you can convert the recordings coming off of that electrode into an audio signal, an audio monitor, and you can hear what they call hash. It's not the hash you smoke, it's the hash you hear. And it sounds like, it just sounds like noise. And in the cortex, eventually you find a stimulus that gets the neuron to spike and fire action potentials that are converted into an auditory stimulus that are very concrete. Crack, crack, crack. Sounds like a bat cracking, like home runs, or outfield balls. When you drop electrodes deeper into the thalamus or into the hypothalamus or into the brainstem areas that control breathing, it's like a machine. You never hear hash. You drop the electrode down. This could be like a grungy old tungsten electrode, not high fidelity electrode, as long as it's got a little bit of insulation on it. You plug it into an audio monitor, it's picking up electricity. And if it's a visual neuron and it's in the thalamus or the retina, and you walk in front of that animal or person, that neuron goes, and then you walk away and it stops. And you put your hand in front of the eye again and it goes, and you could do that for 2 days. And that neuron will just, every time there's a stimulus, it fires. So whereas before, it's a question of how much information is getting up to cortex, and then these abstractions happening where you're creating these ideas. When you go subcortical, everything is...
There's no abstractions.
It's 2 + 2 = 4. There's no abstractions. And this is why I know we have some common friends at Neuralink, and I love the demonstration they did recently. I'm a huge fan of what they're doing and where they're headed. And no, I don't get paid to say that, and I have no business relationship to them. I'm just a huge fan of the people and the mission. But my question was to some of them, when are you going to go subcortical? Because if you want to control an animal, you don't do it in the cortex. The cortex is like the abstract painting I made of your face. Removing one piece or changing something may or may not matter for the abstraction. But when you are in the subcortical areas of the brain, a stimulating electrode can evoke an entire behavior or an entire state. And so the brain, if we're going to have a discussion about the brain and how the brain works, we need to really be clear which brain, because everyone loves neocortex. It's like, oh, canonical circuits in cortex, we're going to get the cortical connectome. And sure, necessary, but not sufficient. Not to be able to plug in patterns of electrical stimulation and get behavior. Eventually we'll get there. But if you're talking subcortical circuits, that's where the action is. That's where you could potentially cure Parkinson's by stimulating the subthalamic nucleus, because we know that it gates motor activation patterns in very predictable ways. So I think for those that are interested in neuroscience, it pays to pay attention to, like, is this a circuit that abstracts the sensory information? Or is it just one that builds up hierarchical models in a very predictable way? And there's a huge chasm in neuroscience right now because there's no conceptual leadership. No one knows which way to go. And this is why I think Neuralink has captured an amazing opportunity, which was, okay, well, while all you academic research labs are figuring all this stuff out, we're going to pick a very specific goal and make the goal the endpoint. And some academic laboratories do that. But I think that's a beautiful way to attack this whole thing about the brain, because it's very concrete. Let's restore motion to the Parkinsonian patient. Academic labs do that, want to do that too, of course. Let's restore speech to the stroke patient. But there's nothing abstract about that. That's about figuring out the solution to a particular problem. So anyway, those are my, and I admit I've mixed in a lot of opinion there, but having spent some time, like 25 years, digging around in the brain and listening to neurons firing and looking at them anatomically, I think given it's 2020, we need to ask the right, the way to get better answers is ask better questions. And the really high level stuff is fun. It makes for good conversation. And it has brought enormous interest. But I think the questions about consciousness and dreaming and stuff, they're fascinating. But I don't know that we're there yet.
So you're saying there might be a chasm in the two views of the power of the brain arising from the circuitry that forms abstractions, or the power of the brain arising from the majority of the circuitry that's just doing very brute force dumb things that are like, that don't have any fancy kind of stuff going on. That's really interesting to think about.
And which one to go after first.
Yeah.
And here
From all
I'm poaching badly from someone I've never met, but whose work I follow, which is, and it was actually on your podcast, I think Elon Musk said, basically the brain is a monkey brain with a supercomputer on top. And I thought that's actually probably the best description of the brain I've ever heard, because it captures a lot of important features like limbic friction, right? We think of like, when we're making plans, we're using the prefrontal cortex and we're executive function and all this kind of stuff. But think about the drug addict who's driven to go pursue heroin or cocaine. They make plans. So clearly they use their frontal cortex. It's just that it's been hijacked by the limbic system and all the monkey brain, as you refer to. It's really not fair to monkeys though, Elon, because actually monkeys can make plans. They just don't make plans as sophisticated as us. I've spent a lot of time with monkeys, but I've also spent a lot of time with humans. Anyway, But
you're saying like there's a lot of value to focusing on the monkey brain, or whatever the heck you call it. Like
I do, because let's say I had an ability to place a chip anywhere I wanted in the brain today, and activate it or inhibit that area. I'm not sure I would put that chip in neocortex, except maybe to just kind of have some fun and see what happens. The reason is it's an abstraction machine, and especially if I wanted to make a mass production tool in mass production that I could give to a lot of people, because it's quite possible that your abstractions are different enough than mine that I wouldn't know what patterns of firing to induce. But if let's say I want to increase my level of focus and creativity, well, then I would love to be able to, for instance, control my level of limbic friction. I would love to be able to wake up and go, oh, you know what? I have an 8 o'clock appointment. I wake up slowly. So between 7 and 8, but I want to do a lot of linear thinking. So you know what? I'm going to turn down the limbic friction or ramp up prefrontal cortex's activation. So there's a lot of stuff that can happen in the thalamus with sensory gating. For instance, you could shut down that shell around the thalamus and allow more creative thinking by allowing more lateral connections. Those would be the experiments I'd want to do. So they're in the subcortical, quote unquote, monkey brain, but you could then look at what sorts of abstract thoughts and behaviors would arise from that. rather than, and here I'm not pointing my finger at Neuralink at all, but there's this obsession with neocortex. But I'm going to, well, I might lose a few friends, but I'll hopefully gain a few. And also, one of the reasons people spend so much time in neocortex,
yes,
I have a fact and an opinion. One fact is that you can image there and you can record there. Right now, the 2-photon and 1-photon microscopy methods that allow you to image deep into the brain still don't allow you to image down really deep unless you're jamming prisms in there and endoscopes. And then the endoscopes are very narrow. So you're getting very, it's like looking at the bottom of the ocean through a spotlight.
Yeah.
And so you much easier look at the waves up on top.
Yep.
Right. So let's face it, folks, a lot of the reasons why there's so many recordings in layer 2, 3 of cortex with all this advanced microscopy is because it's very hard to image deeper. Now, the microscopes are getting better. And thanks to amazing work, mainly of engineers and chemists and physicists, let's face it, they're the ones who brought this revolution to neuroscience in the last 10 years or so. You can image deeper, but we don't really, that's why you see so many reports on layer 2, 3. The other thing, which is purely opinion, and I'm not going after anybody here, but is that as long as there's no clear right answer, it becomes a little easier to do creative work in a structure where no one really knows how it works. So it's fun to probe around because anything you see is novel. If you're going to work in the thalamus or the pulvinar or the hypothalamus or these structures that have been known about since the 60s and 70s and really since the centuries ago, you are dealing with you have to combat existing models.
Yeah.
And whereas in cortex, no one knows how the thing works. The neocortex, 6-layer cortex. And so
everything is valid.
There's a lot more room for discovery.
Yeah.
There's a lot more room for discovery. And I'm not calling anyone out. I love cortex. We've published some papers on cortex. It's super interesting. But I think with the tools that are available nowadays and where people are trying to head of not just reading from the brain, monitoring activity, but writing to the brain, I think we really have to be careful and we need to be thoughtful about what are we trying to write? What script are we trying to write? Because there are many brain structures for which we already know what scripts they write. And I think there's tremendous value there. I don't think it's boring. The fact that they act like machines makes them predictable. Those are your zeros and ones.
Yeah.
Let's start there. But what's sort of happening in this field of writing to the brain is there's this idea. And again, I want to be clear, I'm not pointing at Neuralink. I'm mainly pointing at the neocortical jockeys out there that you go and you observe patterns and then you think replaying those patterns is going to give rise to something interesting.
Yeah.
I should call out one experiment or two experiments which were done by Susumu Tonegawa, Nobel Prize winner from MIT. He's done important work in memory and immunology, of course, is where he got his Nobel, as well as Mark Mayford's lab at UC San Diego. They did an experiment where they monitored a bunch of neurons while an animal learned something. Then they captured those neurons through some molecular tricks so they could replay the neurons. So now there's like perfect case scenario. It's like, okay, you monitor the neurons in your brain. Then I say, okay, neurons 1 through 100 were played in the particular sequence. So you know the space-time, you know the keys on the piano that were played that gave rise to the song, which was the behavior. And then you go back and you reactivate those neurons, except you reactivate them all at once, like slamming on all the keys once on the piano, and you get the exact same behavior. So the space-time code may be meaningless for some structures. Now that's freaky. That's a scary thing because what that means is that all the space-time firing in cortex, the space part may matter more than the time part. So, rate codes and space-time codes, we don't know. And, I'd rather deliver more answers in this discussion than questions, but I think it's an important consideration.
You're saying some of the magic is in the early stages of what the closer to the raw information that the brain is receiving.
I believe so. You know the stimulus, you know the neuron that encodes that stimulus, so you know the transformation. When I say this, for those of you that don't think about sensory transformations, it's like I can show you a red circle, and then I look at how many times the neuron fires in response to that red circle. And then I could show the red circle a bunch of times, green circle, see if it changes. And then essentially the number of times, that is the transformation. You've converted red circle into like 3 action potentials, beep, 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 or whatever you want to call it, for those that think in sound space. So that's what you've created. You know the transformation, and you march up it's called the neuraxis as you go from the periphery up into the cortex. And we know that, and I know Lisa Feldman Barrett, or is it Barrett Feldman?
Barrett Feldman.
Barrett Feldman, excuse me, Lisa, that talked a lot about this, that, birds can do sophisticated things and whatnot as well. But humans, there's a strong, what we call cephalization. A lot of the processing is moved up into the cortex and out of these subcortical areas, but it happens nonetheless. And so as long as you know the transformations, you are in a perfect place to build machines or add machines to the brain that exactly mimic what the brain wants to do, which is take events in the environment and turn them into internal firing of neurons.
So the mastery of the brain can happen at the early level. Another perspective of it is you saying this means that humans aren't that special. If we look at the evolutionary timescale, the leap to intelligence is not that special. So like the extra layers of abstraction isn't where most of the magic happens of intelligence, which gives me hope that maybe if that's true, that means the evolution of intelligence is not that rare of an event.
I certainly hope not.
So you hope there's...
I hope there are other forms of intelligence. I mean, I think what humans are really good at, and here I want to be clear that this is not a formal model, but what humans are really good at is taking that plasma barbell that we were talking about earlier, and not just using it for analysis of space, like your immediate environment, but also using historical information. Like I can read a book today about the history of medicine. I happen to be doing that lately for some stuff I'm researching. And I can take that information, and if I want, I can inject it into my plans for the future. Mm-hmm. Other animals don't seem to do that over the same timescales that we do. Mm-hmm. Now, it may be that the chipmunks are all hiding little like notebooks everywhere in the form of like little dirt castles or something that we don't understand. I mean, the waggle dance of the bee is the most famous example. Mm-hmm. Bees come back to the hive, they orient relative to the honeycomb, and they waggle. There's a guy down in Australia named Srinivasan who studied this. And it's really interesting. No one really understands it, except he understands it best. The bee waggles in a couple ways relative to the orientation of the honeycomb, and then all the other bees see that, it's visual, and they go out and they know the exact coordinate system to get to the source of whatever it was, the food, and bring it back. Mm-hmm. And he's done it where they isolate the bees, he's changed the visual flight environment, all this stuff. They are communicating. Yeah. And they're communicating something about something they saw recently, but it doesn't extend over very long periods of time. The same way that you and I can both read a book, or you can recommend something to me, and then we could converge on a set of ideas later. And in fairness, because she was the one that said it and I didn't, and I hadn't even thought of it. When you talked to Lisa on your podcast, she brought up something beautiful, which is that had never really occurred to me, and I was sort of embarrassed that it hadn't, but it's really beautiful and brilliant, which is that, we don't just encode senses in the form of like color and light and sound waves and taste, but ideas become a form of sensory mapping. And that's where the cool, the really, really cool and exciting stuff is, but we just don't understand what the receptive fields are for ideas. What's an idea receptive field?
And how they're communicated between humans, because we seem to be able to encode those ideas in some kind of way. It's taking all the raw information and the internal physical states, that sensory information, put into this concept blob that we cut in the store, and then we're able to communicate that.
Yeah, your abstractions are different than mine.
Yeah.
I actually think the comment section, on social media is a beautiful example of where the abstractions are different for different people.
Yeah.
So much of the misunderstanding of the world is because of these idea receptive fields. They're not the same. Mm-hmm. Whereas I can look at a photoreceptor neuron or olfactory neuron or a V1 neuron, and I am certain, I would bet my life that yours look and respond exactly the same way that Lisa's do and mine do. Yeah. But once you get beyond there, it gets tricky. And so when you say something or I say something and somebody gets upset about it or even happy about it, their concept of that might be quite a bit different. They don't really know what you mean. They only know what it means to them.
Yeah, so from a Neuralink perspective, it makes sense to optimize the control and the augmentation of the more primitive circuitry. So like the stuff that is closer to the raw sensory information.
Go deeper. By
the way,
go deeper into the brain. And to be fair, so Matt McDougall, who's the neurosurgeon at Neuralink and also awesome. Clinical neurosurgeon, great guy, brilliant. They have amazing people. Yeah. I have to give it to them. They have been very cryptic in recent years. Their website was just like a like nothing there. That they really know how to do things with style, and they've upset a lot of people, but that's good too. But Matt is there. I know Matt. He actually came up through my lab at Stanford, although he was a neurosurgery resident. But he spent time in our lab. He actually came out on the shark dive and did great white shark diving with my lab to collect the VR that we use in our fear stuff. I've talked to Matt, and I think he and other folks there are hungry for the deeper brain structures.
Yeah.
The problem is that damn vasculature, all that blood supply. It's not trivial to get through and down into the brain without damaging the vasculature in the neocortex, which is on the outer crust. But once you start getting into the thalamus and closer to some of the main arterial sources, you really risk getting massive bleeds. And so it's an issue that can be worked out. It just is hard.
This is maybe be nice to educate. I'm showing my ignorance. So the smart stuff is on the surface. So I didn't realize this. I didn't quite realize, because you keep saying deep.
Yeah. So
like the early stages are deep.
Yeah. So
in actually physically in the brain.
Yeah. So the way that of course you got your deep brain structures. They're involved in breathing and heart rate and kind of lizard brain stuff. And then on top of that, this is the model of the brain that no one really subscribes to anymore, but anatomically it works. And then on top, in mammals, and then on top of that, you have the limbic structures, which gate sensory information and decide whether or not you're going to listen to something more than you're going to look at it, or you're going to split your attention to both. Kind of sensory allocation stuff. And then the neocortex is on the outside. And that is where you get a lot of this abstraction stuff. And now not all cortical areas are doing abstraction. Some, like visual area 1, auditory area 1, they're just doing concrete representations. But as you get into the higher order stuff, that when you start hearing names like inferoparietal cortex, and when you start hearing multiple names in the same, then you're talking about higher order areas. But actually, there's an important experiment that drives a lot of what people want to do with brain-machine interface, and that's the work of Bill Newsom, who is at Stanford, and Tony Movshin, who runs the Center for Neuroscience at NYU. This is a wild experiment, and I think it might freak a few people out if they really think about it too deeply. But anyway, here it goes. There's an area called MT in the cortex. And if I showed you a bunch of dots all moving up, and this is what Tony and Bill and some of the other people in that lab did way back when, is they show a bunch of dots moving up. Somewhere in MT, there's some neurons that respond. They fire when the neurons move up. And then what they did is they started varying the coherence of that motion. So they made it so only 50% of the dots moved up and the rest moved randomly. And that neuron fires a little less. And eventually it's random and that neuron stops firing because it's just kind of dots moving everywhere. It's awesome. And there's a systematic map so that other neurons are responding to things moving down and other things are responding left and other things are moving right. Okay. So there's a map of direction space. You go, okay, well, that's great. You could lesion MT. Animals lose the ability to do these kind of coherence discrimination or direction discrimination. But the amazing experiment, the one that just is kind of eerie, is that they lowered a stimulating electrode into MT, found a neuron that responds to when dots go up. But then they silenced that neuron. And sure enough, the animal doesn't recognize the neurons are going up. And then they move the dots down. They stimulate the neuron that responds to things moving up. And the animal responds, because it can't speak, it responds by doing a lever press, which says the dots are moving up. So in other words, the dots are moving down in reality on the computer screen. They're stimulating the neuron that responds to dots moving up. And the perception of the animal is that dots are moving up, which tells you that your perception of external reality absolutely has to be a neuronal abstraction. It is not tacked to the movement of the dots in any absolute way. Your perception of the outside world depends entirely on the activation patterns of neurons in the brain. And you could hear that and say, well, duh, because if I stimulate, the stretch reflex and you kick or something or whatever, the knee reflex and you kick, of course, there's a neuron that triggers that, but it didn't have to be that way.
Yeah. Because
A, the animal had prior experience. B, you're way up in this, higher order cortical areas. What this means is that, and I generally try and avoid conversations about this kind of thing, but what this means is that we are constructing our reality with this space-time firing the zeros and ones, and it doesn't have to have anything to do with the actual reality. And the animal or person can be absolutely convinced that that's what's happening.
Are you familiar with the work of Donald Hoffman? So he makes an evolutionary argument that's not important of that our brains are completely detached from reality, in the sense that he makes a radical case that we have no idea what physical reality is, and in fact it's drastically different than what we think it is.
Oh my.
So he goes,
that's scary.
So he doesn't say like there's just, because you're kind of implying there's a gap. There might be a gap. We're constructing an illusion, and then maybe using communication to maybe create a consistency that's sufficient for our human collaboration, whatever, or mammal, just maybe even just life forms are constructing a consistent reality that's maybe detached. I mean, that's really cool that neurons are constructing that, like that you can prove that. This is what neuroscience at its best, vision science. But he says that like our brain is actually just lost its shit on the path of evolution, to where we're just playing games with each other in constructing realities that allow our survival, but it's completely detached from physical reality.
Like we're missing a lot.
We're missing like most of it, if not all of it.
Well, this was it's fascinating because I just saw the Oliver Sacks documentary. There's a new documentary out about his life. And there's this one part where he's like, I've spent part of my life trying to imagine what it would like to be a bat or something, to see the world through the life, the sensory apparatus of a bat. And he did this with these patients that were locked into these horrible syndromes, that to pull out some of the beauty of their experience as well, not just communicate the suffering, although the suffering too. And as I was listening to him talk about this, I started to realize, it's like, well, what, like there are these mantis shrimps that can see 60 shades of pink or something. And they see this stuff all the time, and animals that can see UV light. Every time I learn about an animal that can sense other things in the environment that I can't, like heat sensing, I don't crave that experience the same way Sachs talked about craving that experience. But it does throw another penny in the jar for what you're saying, which is that it could be that most, if not all, of what I perceive and believe is just a neural fabrication. And that for better or for worse, we all agree on enough of the same neural fabrications in the same time and place that we're able to function.
Not only that, but we agree with the things that are trying to eat us enough to where they don't eat us, meaning like that it's not just us humans, right?
I see, because it's interactive.
It's interactive. Now I think it's a really nice thought experiment. I think because Donald really frames it in a scientific, like he makes a hard, like as hard as our discussion has been now, he makes a hard scientific case that we don't know shit about reality. I think that's a little bit hardcore, but I think it's I think
it's hardcore. It's hardcore.
I think it's a good thought experiment that kind of cleanses the palate of the confidence we might have about because we are operating in this abstraction space, and the sensory spaces might be something very different. And it's kind of interesting to think about if you start to go into the realm of Neuralink, or start to talk about just everything that you've been talking about with dream states and psychedelics and stuff like that. Which layer can we control and play around with to maybe look into a different slice of reality? You
just got to do the experiment. The key is to just do the experiment in the most ethical way possible. That's the beauty of experiments. This is why, there's wonderful theoretical neuroscience happening now to make predictions, but that's why experimental science is so wonderful. You can go into the laboratory and poke around in there and be a brain explorer and listen to and write to neurons. And when you do that, you get answers. You don't always get the answers you want, but that's the beauty of it. I think when you were saying this thing about reality and the Donald Hoffman model, I was thinking about children, like when I have an older sister, she's very sane. But when she was a kid, she had an imaginary friend.
Yeah.
And she would play with this imaginary friend. And there was a consistency. This friend was like, it was Larry, lived in a purple house. Larry was a girl. It was like all this stuff that a young child wouldn't have any issue with. And then one day she announced that Larry had died, right? And it wasn't dramatic. And that was it. And she just stopped. And I always wonder what that neurodevelopmental event was that kept her out of a psychiatric ward had she kept that imaginary friend. Yeah. But it's also, there was something kind of sad to it. I think the way it was told to me, because I'm the younger brother, I wasn't around for that. But my dad told me that there was a kind of a sadness because it was this beautiful reality that had been constructed. And so we kind of I wonder, as you're telling me this, whether or not, as adults, we try and create as much reality for children as we can so that they can make predictions and feel safe, because the ability to make predictions is a lot of what keeps our autonomic arousal in check. I mean, we go to sleep every night and we give up total control, and that should frighten us deeply. But, unfortunately, autonomic arousal yanks us down under, and we don't negotiate too much. So you sleep sooner or later. I don't know. I was a little worried we'd get into discussions about the nature of reality, because it's interesting in the laboratory. I'm a very much like, what's the experiment? Yes. What would what's the analysis going to look like? What mutant mouse are we going to use? What experience are we going to put someone through? But I think it's wonderful that in 2020, we can finally have discussions about this stuff and peek around the corner and say, well, Neuralink and others who are doing similar things are going to figure it out. They're going to, the answers will show up, and we just have to be open to interpretation.
Do you think there could be an experiment centered around consciousness? I mean, you're plugged into the neuroscience community. I think for the longest time, the quote unquote C word was totally was almost anti-scientific. But now more and more people are talking about consciousness. Elon is talking about consciousness. AI folks are talking about consciousness. It's still, nobody knows anything, but it feels like a legitimate domain of inquiry that's hungry for a real experiment.
So I have, fortunately, 3 short answers to this.
Right.
The first one is
2 hours later.
I'm not particularly succinct. I agree. The joke I always tell is, there are 2 things you never want to say to a scientist. One is, what do you do? And the second one is, take as much time as you need. And you definitely don't want to say them in the same sentence. I have 3 short answers to it. So there's a cynical answer, kind of, and it's not one I enjoy giving, which is that if you look into the 70s and back at the 1970s and 1980s, and even into the early 2000s, there were some very dynamic, very impressive speakers who were very smart in the field of neuroscience and related fields, who thought hard about the consciousness problem and fell in love with the problem, but overlooked the fact that the technology wasn't there. Yeah. So I admire them for falling in love with the problem, but they gleaned tremendous taxpayer resources essentially for nothing. And these people know who they are. Some of them are alive, some of them aren't. I'm not referring to Francis Crick, who was brilliant, by the way, and thought the claustrum was involved in consciousness, which I think is a great idea. It's this obscure structure that no one's really studied. People are now starting to study it. So I think Francis was brilliant and wonderful. But there were books written about it. It makes for great television stuff and thought around the table or after a couple glasses of wine or whatever. It's an important problem nonetheless. And so I do think the consciousness, the issue is it's not operationally defined, right? That psychologists are much smarter than a lot of hard scientists in that, for the following reason. They put operational definitions. They know that psychology, if we're talking about motivation, for instance, they know they need to put operational definitions on that so that 2 laboratories can know they're studying the same thing. The problem with consciousness is no one can agree on what that is. And this was a problem for attention. when I was coming up. So in the early 2000s, people would argue, what is attention? Is it spatial attention, auditory attention? Is it? And finally, people were like, you know what? We agree.
Have they agreed on that one?
Sort
I remember,
sort of.
I remember
Sort of.
hearing people scream about attention.
Right. They couldn't even agree on attention. So I was coming up as a young graduate student. I'm thinking like, I'm definitely not going to work on attention, and I'm definitely not going to work on consciousness. And I wanted something that I could solve or figure out. I want to be able to see the circuit or the neurons. I want to be able to hear it on the audio. I want to record from it. And then I want to do gain of function and loss of function. Take it away, see something change, put it back, see something change in a systematic way. And that takes you down into the depths of some stuff that's pretty plug and chug, you know. Yeah. But, you know, I'll borrow from something in the military because I'm fortunate to do some work with units from special operations, and they have beautiful language around things because their world is not abstract. Mm-hmm. And they talk about 3-meter targets, 10-meter targets, and 100-meter targets. And it's not an issue of picking the 100-meter target because it's more beautiful or because it's more interesting. If you don't take down the 3-meter targets and the 10-meter targets first, you're dead. So that's I think scientists could pay to, you know, adopt a more kind of military thinking in that sense. The other thing that is really important is that just because somebody conceived of something and can talk about it beautifully and can glean a lot of resources for it, doesn't mean that it's led anywhere. So, but this isn't just true of the consciousness issue. And I don't want to sound cynical, but I could pull up some names of molecules that occupied hundreds of articles in the very premier journals that then were later discovered to be totally moot for that process. And biotech companies folded, everyone, and the lab pivots and starts doing something different with that molecule. Mm-hmm. And nobody talks about it. Right. Because as long as you're in the game, we have this thing called anonymous peer review. You can't afford to piss off anybody too much unless you have some other funding stream. And I've avoided battles most of my career, but I pay attention to all of it. And I've watched this, and I don't think it's ego driven. I think it's that people fall in love with an idea. I don't think there's not enough money in science for people to sit back there rubbing their hands together. You know, the beauty of what Neuralink and Elon and team, because obviously he's very impressive, but the team as a whole is really what gives me great confidence in their mission, is that he's already got enough money, so it can't be about that. He doesn't seem to need it at a level of I don't know him, but he doesn't seem to need it at a kind of an ego level or something. I think it's driven by genuine curiosity, and the team that he's assembled include people that are very kind of abstract neocortex space-time coding people. They're people like Matt, who is a neurosurgeon. You can't BS neurosurgery. Yeah. Failures in neurosurgery are not tolerated. So you have to be very good to exceptional to even get through the gate. And he's exceptional. And then they've got people like Dan Adams, who was at UCSF for a long time, is a good friend and I've known him for years, who is very concrete, studied the vasculature in the eye and how it maps to the vasculature in cortex. When you get a team like that together, you're going to have dissenters. You're going to have people that are high-level thinkers, people that are coders. Yeah. When you get a team like that, it no longer looks like an academic laboratory or even a field in science. And so I think they're going to solve some really hard problems. And again, I'm not here. I have nothing at stake with them. But I think that's the solution. You need a bunch of people who don't need first author papers, who don't need to complete their PhD, who aren't relying on outside funding, who have a clear mission, and you have a bunch of people who are basically will adapt to solve the problem.
I like the analogy of the 3-meter target and the 100-meter target. So the folks at Neuralink are basically, many of them are some of the best people in the world at the 3-meter target. Like you mentioned Matt, neurosurgery, like they're solving real problems. There's no BS philosophical, smoke some weed and look at the stars. But so both on Elon and because I think like this, I think it's really important to think about the 100-meter, and the 100-meter is not even 100-meter, but like like the stuff behind the hill that's too far away, which is where I put consciousness. Maybe I tend to believe that consciousness can be engineered. I think part of the business I want to build leverages that idea that consciousness is a lot simpler than we've been talking about.
Well, if someone can simplify the problem,
Right.
that will be wonderful. I mean, the reason we can talk about something as abstract as face representations in fusiform face area is because Nancy Canwisher had the brilliance to tie it to the kind of lower level statistics of visual scenes. It wasn't because she was like, oh, I bet it's there. Yep. That wouldn't have been interesting. So people like her understand how to bridge that gap, and they put a tractable definition. Right. So that's what I'm begging for in science is a tractable definition.
But I want people to sit in I want people who are really uncomfortable with woo-woo, like consciousness, like high-level stuff, to sit in that topic and sit uncomfortably, because it forces them to then try to ground and simplify it into something that's concrete. Because too many people are just uncomfortable to sit in the consciousness room because there's no definitions. It's like attention or intelligence in the artificial intelligence community. But the reality is, it's easy to avoid that room altogether, which is what, I mean, there's analogies to everything you've said with the artificial intelligence community, with Minsky and even Alan Turing that talked about intelligence a lot. And then they drew a lot of funding and then it crashed because they really didn't do anything with it. And it was a lot of force of personality and so on. But that doesn't mean the topic of the Turing test and intelligence isn't something we should sit on and think like, what is, well, first of all, I mean, Turing actually attempted this with the Turing test. He tried to make concrete this very question of intelligence. It doesn't mean that we shouldn't linger on it. And we shouldn't forget that ultimately that is what our efforts are all about in the artificial intelligence community and in the people, whether it's neuroscience or whatever bigger umbrella you want to use for understanding the mind. The goal is not just about understanding layer 2 or 3 of the vision. It's to understand consciousness and intelligence and maybe create it, or just all the possible biggest questions of our universe. That's ultimately the dream.
Absolutely. And I think what I really appreciate about what you're saying is that everybody, whether or not they're working on a kind of a low-level synapse that's like a reflex in the musculature or something very high-level abstract, can benefit from looking at those who prefer everyone's going after 3 meter, 10 meter, and 100 meter targets in some sense, but to be able to tolerate the discomfort of being in a conversation where there are real answers, where the zeros and ones are known, zeros and ones, are those the equivalent of that in the nervous system. And also, as you said, for the people that are very much like, oh, I can only trust what I can see and touch, those people need to put themselves into the discomfort of the high-level conversation, because what's missing is conversation and conceptualization of things at multiple levels. I think I don't gripe about, my lab's been fortunate. We've been funded from the start and we've been happy in that regard and lucky, and we're grateful for that. But I think one of the challenges of research being so expensive is that there isn't a lot of time, especially nowadays, for people to just convene around a topic, because there's so much emphasis on productivity. And so there are actually, believe it or not, there aren't that many formal concepts in neuroscience right now. The last 10 years has been this huge influx of tools. Mm-hmm. And so people have been neural circuits and probing around and connectomes, and it's been wonderful. Yeah. But 10, 20 years ago, when the consciousness stuff was more prominent, the C word, as you said, mm-hmm. What was good about that time is that people would go to meetings and actually discuss ideas and models. Now it's sort of like demonstration day at the school science fair, where everyone's got their thing and some stuff is cooler than others. But I think we're going to see a shift. I'm grateful that we have so many computer scientists and theoreticians and or theorists, I think they call themselves. Somebody tell me what the difference is someday. And psychology and even, dare I say, philosophy, these things are starting to converge. Neuroscience, the name neuroscience, there wasn't even such a thing when I started graduate school or as a postdoc. It was neurophysiology, or you were a neuroanatomist or what. Now, it's sort of everybody's invited, and that's beautiful. That means that something's useful is going to come of all this. And there's also tremendous work, of course, happening for the treatment of disease, and we shouldn't overlook that. That's where, eliminating, reducing suffering is also a huge initiative in neuroscience. So there's a lot of beauty in the field, but the consciousness thing continues to be it's like an exotic bird. It's like no one really quite knows how to handle it, and it dies very easily.
Well, yeah.
So,
I think also from the AI perspective, I view the brain as less sacred. I think from a neuroscience perspective, you're a little bit more sensitive to BS, like BS narratives about the brain or whatever. I'm a little bit more comfortable with just poetic BS about the brain, as long as it helps engineer intelligent systems.
Well,
you know what I mean?
And I have to, I confess ignorance when it comes to, most things about coding, and I'm have some quantitative ability, but I don't have strong quantitative leanings, and so I know my limitations too. And so I think the next generation coming up, a lot of the students at Stanford are really interested in quantitative models and theory and AI. And I remember when I was coming up, a lot of the people who were doing work ahead of me, I kind of rolled my eyes at some of the stuff they were doing, including some of their personalities, although I have many great senior colleagues everywhere.
Way of the world.
So it's the way of the world. So nobody knows what it's like to be a young graduate student in 2020, except the young graduate student. So I know what I know there are a lot of things I don't know. And in addition to wanting to do a lot of public education, increase scientific literacy and neuroscientific thinking, et cetera, a big goal of mine is to try and at least pave the way so that these really brilliant and forward-thinking younger scientists can make the biggest possible dent and make what will eventually be all us old guys and gals look stupid. I mean, that's what we were all trying to do.
Goal.
That's what we were trying to do. So, yeah.
So from the highest possible topic of consciousness to the lowest level topic of David Goggins, let's
I don't know if it's low level. He's high performance.
High performance,
Right.
but like low, like there's no, I don't think David has any time for philosophy. Let's just put it this way.
Well, I think we can tack it to what we were just saying in a meaningful way, which is whatever goes on in that abstraction part of the brain,
Mm-hmm.
he's figured out how to dig down in whatever the limbic friction.
Yeah.
He's figured out how to grab a hold of that, scruff it, and send it in the direction that he's decided it needs to go. And what's wild is that what we're talking about is him doing that to himself, right? It's like he's scruffing himself and directing himself in a particular direction and sending himself down that trajectory. And what's beautiful is that he acknowledges that process is not pretty. It doesn't feel good. It's kind of horrible at every level, but he's created this rewarding element to it. And I think that's what's so, it's so admirable. And it's what so many people crave, which is regulation of the self at that level.
And he practices, I mean, there's a ritual to it. There's every single day, like no exceptions. There's a practice aspect to the suffering that he goes through.
It's principled suffering.
Principled suffering.
It is.
And I mean, I admire all aspects of it, including him and his girlfriend / wife. I'm not sure. Should probably know this.
I don't know.
Fiance.
Wonderful person.
I'm not asking him.
No. We've only communicated. I've only communicated with her via text about some stuff. I was asking David, but yeah, they clearly have formed a powerful team.
Yeah.
And it's
Good cop and
a
bad
beautiful
cop.
thing to see people working in that kind of synergy.
It's inspiring to me, same as with Elon, that a guy like David Goggins can find love. That you find a thing that works, which gives me hope that like whatever flavor of crazy I am, you can always find another thing that works with that. But I've had so maybe let's trade Goggins stories. You from a neuroscience perspective, me from a self-inflicted pain perspective. I somehow found myself in communication with David about some challenges that I was undergoing. One of which is we were communicating every single day, email, phone, about a particular 30-day challenge that I did that stretched for longer, of push-ups and pull-ups.
You made a call out on social
Yeah,
media.
social media. It was
Actually,
dumb.
I think that
All
was
of it was
the
dumb.
point. I knew of you before, but that's where I started tracking some of what you were doing with these physical challenges. And
Yeah. The hell's wrong with that guy?
well, no, I think I don't often comment on people's stuff, but I think I commented something like neural plasticity loves a non-negotiable rule. Or no, I said a non-negotiable contract. Because
That's a good
at the
line.
point where,
That's a good line.
neuroplasticity really loves a non-negotiable contract because, and I've said this before, so forgive me, but, the brain is doing analysis of duration, path, and outcome. And that's a lot of work for the brain. And the more that it can pass off duration, path, and outcome to just reflex, the more energy and it can allocate to other things. So if you decide, there's no negotiation about how many push-ups, how far I'm going to run, how many days, how many pull-ups, et cetera. You actually have more energy for push-ups, running, and pull-ups.
And when you say neuroplasticity, you mean like the brain, once the decision is made, it'll start rewiring stuff to make sure that we can actually make this happen.
That's right. I mean, so much of what we do is reflexive at the level of just core circuitry, breathing, heart rate, all that boring stuff, digestion. But then there's a lot of reflexive stuff like how you drink out of a mug of coffee that's reflexive too, but that you had to learn at some point in your life earlier when you were very little, analyzing duration, path, and outcome. And that involved a lot of top-down processing with the prefrontal cortex. But through plasticity mechanisms, you now do it. So when you take on a challenge, provided that you understand the core mechanics of how to, run push-ups and pull-ups and whatever else you decided to do, once you set the number and the duration and all that, then all you have to do is just go. But people get caught in that tide pool of just, well, do I really have to do it? How do I not do that? What if I get injured? What if I, can I sneak a this or that, and that's work.
Yeah.
And to some extent, I not David Goggins, obviously, nor do I claim to understand his process, partially, but maybe a little bit, which is that it's clear that by making the decision, there's more resources to devote to the effort of the actual execution.
Well, that's a really, like what you're saying was not a lesson that was obvious to me, and it's still not obvious. It's something I really work at, which is there is always an option to quit. And I mean, that's something I really struggle with. I mean, I've quit some things in my life, just like stupid stuff. And one lesson I've learned is if you quit once, it opens the door that, like, it's really valuable to trick your brain into thinking that you're gonna have to die before you quit. Like, it's actually really convenient. So actually what you're saying is very profound, but you shouldn't intellectualize it. Like, it took me time to develop, like, psychologically, in ways that I think it would be another conversation, because I'm not sure how to put it into words, but it's really tough on me to do certain parts of that challenge.
Well, it was a huge output.
The number that, I thought the number would be hard, but it's not. It's the entirety of it, especially in the early days, was just spending. I'm kind of embarrassed to say how many hours this took. So I didn't say publicly how many hours, because I knew people would be like, aren't you supposed to do other stuff? Like,
well, it's
the hell are you doing?
Again, I don't want to speculate too much about, but occasionally David has said this publicly, where people will be like, "Don't you sleep or something?"
Yeah.
And his process used to just be that he would just block, delete,
Yeah.
like gone. But it's actually it's a super interesting topic, and because self-control and directing our actions and the role of emotion and quitting, these are vital to the human experience, and they're vital to performing well at anything. And at a high, obviously at a super high level, being able to understand this about the self is crucial. So I have a friend who was also in the teams. His name is Pat Dossett. He did 9 years in the SEAL teams. And in a similar way, there's a lore about him among team guys, because of a kind of funny challenge he gave himself, which was, so he and I swim together, although he swims further up front than I do, and he's very patient. But he was he was assigned when he was in the teams to a position that gave him a little more time behind a desk than he wanted, and is not as much time out in deployments, although he did deployments. So he didn't know what to do at that time, but he thought about it and he asked himself, what does he hate the most? Mm-hmm. And it turns out the thing that he hated doing the most was bear crawls, walking on your hands and knees. So he decided to bear crawl for a mile for time. So he was bear crawling a mile a day, right? And I thought that was an interesting example they gave because, why pick the thing you hate the most? And I think it maps right back to limbic friction. It's the thing that creates the most limbic friction. And so if you can overcome that, then there's carryover. And I think the notion of carryover has been talked about psychologically and kind of in the self-help space, like, oh, if you run a marathon, it's going to help you in other areas of life. But will it really? Will it? Well, I think it depends on whether or not there's a lot of limbic friction, because if there is, what you're exercising is not a circuit for bear crawls or a circuit for pull-ups. What you're doing is you're exercising a circuit for top-down control. And that circuit was not designed to be for bear crawls or pull-ups or coding or waking up in the middle of the night to do something hard. That circuit was designed to override limbic friction. And so neural circuits were designed to generalize, right? The stress response to an incoming threat that's a physical threat was designed to feel the same way and be the same response internally as the threat to an impending exam or divorce or marriage or whatever it is that's stressing somebody out. And so neural circuits are not designed to be for one particular action or purpose. So if you can, as you did, if you can train up top-down control under conditions of the highest limbic friction, that when the desire to quit is at its utmost, either because of fatigue or hyperarousal, being too stressed or too tired, you're learning how to engage a circuit, and that circuit is forever with you. And if you don't engage it, it sits there, but it's atrophied. It's like a plant that doesn't get any water. And a lot of this has been discussed in self-help and growth mindset and all these kinds of ideas that circle the internet and social media. But when you start to think about how they map to neural circuits, I think there's some utility, because what it means is that the limbic friction that you'll experience in, I don't know, maybe some future relationship to something or someone, it's a category of neural processing that should immediately click into place. It's just like the limbic friction you experienced trying to engage in the God knows how many push-ups, pull-ups, and running runs you were doing.
25,000. Who's counting?
So, folks, if Lex does this again, more comments, more likes.
No, well,
this is the problem with you getting more followers, is you're going to
get more. Yeah.
Actually, I should say that's the benefit. I don't know. Maybe it's not politically correct for me to ask, but there is this stereotype about Russians being,
politically correct.
No, like being really durable. And I started going to that Russian banya that way back before COVID, and they could tolerate a lot of heat, and they would sit very stoic, no one was going, oh, it's hot in here. They would just kind of ease into it. So maybe there's something there. Who knows?
Might be something there, but it could be also just personal. I just have I found myself, everyone's different, but I've found myself to be able to do something unpleasant for very long periods of time. Like, I'm able to shut off the mind, and I don't think that's been fully tested. And I
monkey mind or the supercomputer?
Well, it's interesting. I mean, which mind tells you to quit exactly?
Limbic friction tells you.
Well, the limbic friction is the source of that, but who are you talking with exactly?
So there's we can put something very concrete to that. So there's a paper published in Cell, super top tier journal, 2 years ago, looking at effort. And this was in a visual environment of trying to swim forward toward a target and a reward. And it was a really cool experiment because they manipulated virtually the visual environment. So the same amount of effort was being expended every time, but sometimes the perception was you're making forward progress, and sometimes the perception was you're making no progress because stuff wasn't drifting by, meant no progress. So you could be swimming and you're not making progress. And it turns out that with each bout of effort, there's a epinephrine and norepinephrine is being released in the brainstem. And glia, these what traditionally were thought of as support cells for the neurons, but they do a lot of things actively too, are measuring the amount of epinephrine and norepinephrine in that circuit. And when it exceeds a certain threshold, the glia send inhibitory signals that shut down top-down control. They literally, it's the you quit, you stop. There's no more. It's you quit enduring. It can be rescued. Endurance can be rescued with dopamine. So that's where the subjective part really comes into play. So you quit because you've learned how to turn that off, or you've learned how to, some people will reward the pain process so much that friction becomes the reward. And when you talk about people like Goggins and other people I know from special operations, and people have gone through cancer treatments 3 times, you hear about, just when you hear about people, the Viktor Frankl stories, I mean, you hear about Nelson Mandela, you hear about these stories, I'm sure the same process is involved. Mm-hmm. Again, this speaks to the generalizability of these processes as opposed to a neural circuit for a particular action or cognitive function. So I think you have to learn to subjectively self-reward in a way that replenishes you. Goggins talks about eating souls. It's a very dramatic example. In his mind, apparently, that's a form of reward, but it's not just a form of reward where you're picking up a trophy or something. It's actually, it gives you energy. It's a reward that gives more neural energy. And I'm defining that as more dopamine to suppress the noradrenaline and adrenaline circuits in the brainstem.
So ultimately maps to that. Yeah, he creates enemies. He's always fighting enemies. I think I have enemies, but they're usually just versions of me inside my head. So I've thought about it. Through that 30-day challenge, I tried to come up with like fake enemies, and it wasn't working. The only enemy I came up with is David.
Well, now you certainly have a formidable adversary in this one.
I don't care. Yeah. David. I'm willing to die on this one. So let's go there. But
let's hope you both survive this one.
Well, but my problem is the physical. There's so everything we've been talking about been the mind. There's a physical aspect that's just practically difficult, which is like I can't when you injure yourself at a certain point, like you just can't function.
Or you're doing more damage. Yeah, you're talking about taking yourself out of running for
for the rest of your life potentially, or or for years. So, I'd love to avoid that. Mm-hmm. Right? There's just like stupid physical stuff that you just want to avoid. Mm-hmm. You want to keep it purely in the mental, and if it's purely in the mental, that's when the race is interesting. But yeah, the problem with these physical challenges, as David has experienced, I mean, it has a toll on your body. Mm-hmm. I tend to think of the mind as limitless, and the body is kind of, unfortunately, quite limited.
Well, I think the key is to dynamically control your output, and that can be done by reducing effort, which doesn't work throughout, but also by restoring through these subjective reward processes. Yeah. And we don't want to go down the rabbit hole of why this all works, but these are ancient pathways that were designed to bring resources to an animal or to a person through foraging for hunting or mates or water or all these things. And they work so well because they're down in those circuits where we know the zeros and ones. And that's great because it can be subjective at the level of, I reached this one milestone, this one horizon, this 1 3-meter target. But if you don't reward it, it's just effort. If you do self-reward it, it's effort -1 in terms of the adrenaline output.
I have to ask you about this. You're one of the great communicators in science. I'm really a big fan of yours, enjoying in terms of like the educational stuff you're putting on neuroscience.
Thank you.
What's the do you have a philosophy behind it, or is it just an instinct? Unstoppable force? Do you have what's your thinking? Because it's rare and it's exciting. I'm excited that somebody from Stanford. So I'm in multiple places in the sense of like where my interests lie, and one, politically speaking, academic institutions are under fire. for many reasons we don't need to get into. I get into in a lot of other places, but I believe in places like Stanford and places like MIT as one of the most magical institutions for inspiring people to dream, people to build the future. I mean, I believe that it is a really special, these universities are really special places. And so it's always exciting to me when somebody as inspiring as you represents those places. So it makes me proud that somebody from Stanford is like somebody like you is representing Stanford. So maybe you could speak to what's how did you come to be who you are in being a communicator?
Well, first of all, thanks for the kind words, especially coming from you. I think Stanford is an amazing place, as is MIT, and it's such a
MIT is better, by the way. It's okay. I'll let it out. Anything you say at this point.
I have many friends at MIT.
Yeah,
hi Ed.
Smarter
Boyden.
Friends. Yeah,
Ed Boyden is best in class. Among the best in class. There's some people, not me, that can hold a candle to him, but not many. Maybe one or two. Yeah. I think the great benefit of being in a place like MIT or Stanford is that when you look around, the average is very high, right? You have many best in class among the one or two or three best in the world at what they do, and it's a wonderful privilege to be there. And one thing that I think also makes them and other universities like them very special is that there's an emphasis on what gets exported out of the university, not keeping it ivory tower, and really trying to keep an eye on what's needed in the world and trying to do something useful. And I think the proximity to industry in Silicon Valley and in the Boston area and Cambridge also lends itself well to that. And there are other institutions too, of course. So the reason I got involved in educating on social media was actually because of a Pat Dossett, the Bear Call guy. Mm-hmm. It was at the turn of 2018 to 2019. We had formed a good friendship, and he talked me into doing these early morning cold water swims. I was learning a lot about pain and suffering, but also the beauty of cold water swims. And we were talking one morning, and he said, so what are you going to do to serve the world in 2019? It's like, that's the way that like a Texan former SEAL talks. Like, we're just literally like, what are you going to do to serve the world in 2019? Like, well, I run my lab. It's like, no, what are you going to do that's new? And he wasn't forceful in it, but I was like, oh, that's an interesting question. I said, well, if I had my way, I would just, teach everyone about the brain, because I think it's amazing. He goes, well, do it. And I go, all right. He goes, shake on it. So we did it, and so I started putting out these posts, and it's grown into to include a variety of things. But you asked about a governing philosophy. So I want to increase interest in the brain and in the nervous system and in biology generally. That's one major goal. I'd like to increase scientific literacy, which can't be rammed down people's throats of talking about how to look at a graph and statistics and, z-scores and p-values and genetics. It has to be done gradually, in my opinion. I want to put valuable tools into the world, mainly tools that map to things that we're doing in our lab. So these will be tools centered around how to understand and direct one's states of mind and body. So reduce stress, raise one's stress threshold. So it's not always just about being calm. Sometimes it's about learning how to tolerate not calm. Raise awareness for mental health. I mean, there's a ton of micro missions in this, but it all really maps back to, like the 8 and 10-year-old version of me, which is I used to spend my weekends when I was a kid reading about weird animals. And I had this obsession with like medieval weapons and stuff like catapults. And then I used to come into school on Monday and I would ask if I could talk about it to the class and teach. And it's really, I promise, and some people might not believe me, but it's really, I don't really like being the point of focus. I just get so excited about these gems that I find in the world, in books and in experiments and in discussions with colleagues and discussions with people like you and around the universe. And I can't just compulsively, I got to tell people about it. Yeah. So I try and package it into a form that people can access. I think I think the reception has been really wonderful. Stanford has been very supportive, thankfully. I've done some podcasts even with them, and they've reposted some stuff on social media. It's a precarious place to put yourself out there as a research academic. I think some of my colleagues, both locally and elsewhere, probably wonder if I'm still serious about research, which I absolutely am. And I also acknowledge that, their research and the research coming out of the field needs to be talked about. And not all scientists are good at translating that into a language that people can access. And I don't like the phrase dumb it down. What I like to do is take a concept that I think people will find interesting and useful and offer it sort of like you would offer food to somebody visiting your home. You're not going to cram foie gras in their face. You're going to say, like, do you want a cracker? Like, and they say, yeah. And like, do you want something on that cracker? Like, do you like cheese? Like, yeah. Like, do you want Swiss cheese, or you want that really like stinky, like French? I don't like cheese much, but, or do you want foie gras? Like, what's that? Like, so you're trying, the best information prompts more questions of interest, not questions of confusion, but questions of interest. And so I feel like one door opens, then another door opens, then another door opens. And pretty soon, the image in my mind is you create a bunch of neuroscientists who are thinking about themselves neuroscientifically. And I don't begin to think that I have all the answers at all. I cast a neuroscience, sometimes a little bit of a psychology lens onto what I think are interesting topics. And, someday I'm going to go into the ground or the ocean or wherever it is I end up. And I'm very comfortable with the fact that not everyone's going to be happy with how I deliver the information, but I would hope that people would feel like some of it was useful and meaningful and got them to think a little bit harder.
Since you mentioned going into the ground and Viktor Frankl, Man's Search for Meaning, I reread that book quite often. Let me ask the big ridiculous question about life. What do you think is the meaning of it all? Like, and maybe why do you mention that book from a psychologist perspective, which Viktor Frankl was, or do you ever think about the bigger philosophical questions it raises about meaning? And the meaning of it all?
One of the great challenges in assigning giving a good answer to the question of like, what's the meaning of life is, I think, illustrated best by the Viktor Frankl example, although there are other examples too, which is that our sense of meaning is very elastic in time and space. And we talked a little bit about this earlier, but it's amazing to me that somebody locked in a cell or a concentration camp can bring the horizon in close enough that they can then micro slice their environment so that they can find rewards and meaning and power and beauty, even in a little square box or a horrible situation. And I think this really speaks to one of the most important features of the human mind, which is let's take two opposite extremes. One would be, let's say the alarm went off right now in this building and the building started shaking. Our vision, our hearing, everything would be tuned to this space-time bubble for those moments. Mm-hmm. And everything that we would process, all that would matter, the only meaning would be get out of here safe, figure out what's going on, contact loved ones, etc. If we were to sit back totally relaxed, we could do I think it's called pale blue dot thing or whatever, where we could imagine ourselves in this room and then they were in the United States and this continent and the earth and then it's peering down us. Mm-hmm. And all of a sudden you get back, it can seem so big that all of a sudden it's meaningless, right? If you see yourself as just one brief glimmer in all of time and all of space, you go to, I don't matter. And if you go to, every little thing that happens in this text thread or this, comment section on YouTube or Instagram, your space-time bubble is tiny, mm-hmm. then everything seems inflated. And the brain will contract and dilate its space-time vision and time, but also sense of meaning. And that's beautiful. And it's what allows us to be so dynamic in different environments. And we can pull from the past and the present and future. It's why examples like Nelson Mandela and Viktor Frankl had to include. It makes sense that it wasn't just about grinding it out. They had to find those dopamine rewards, even in those little boxes they were forced into. So I'm not trying to dodge an answer, but for me personally, and I think about this a lot because I have this complicated history in science where my undergraduate, graduate advisor, and postdoctoral advisor all died young. So, and they were wonderful people and had immense importance in my life. But what I realized is that we can get so fixated on the thing that we're experiencing holding tremendous meaning, but it only holds that meaning for as long as we're in that space-time regime. And this is important because what really gives meaning is the understanding that you can move between these different space-time dimensionalities. And I'm not trying to sound like a theoretical physicist or anyone that thinks about the cosmos in saying that. It's really the fact that sometimes we say and do and think things and it feels so important. And then 2 days later, we're like, oh, what happened? Well, you had a different brain processing algorithm entirely. You were in a completely different state. And so what I want to do in this lifetime is I want to engage in as many different levels of contraction and dilation of meaning as possible. I want to go to the micro. I sometimes think about this. I'm like, if I just pulled over the side of the road, I bet you there's an anthill there and their whole world is fascinating. You can't stay there. And you also can't stay staring up at the clouds and just think about how we're just these little beings and it doesn't matter. The key is the journey back and forth, up and down that staircase, back and forth and back and forth. And my goal is to get as many trips up and down that staircase as I can before the Reaper comes for me.
Oh, beautiful. So the dance of dilation and contraction between the different space, the zoom in, zoom out, and get as many steps in on that staircase.
That's my goal anyway. And I've watched people die. I watched my postdoc advisor die, wither away, my graduate advisor. It was tragic, but they found beauty in these closing moments because their bubble was their kids in one case, or like one of them was a Giants fan and like got to see a Giants game, in her last moments. And you just realize like it's a Giants game, but not in that moment because time is closing. And so those time bins feel huge because she's slicing things so differently. So I think learning how to do that better and more fluidly, recognizing where one is and not getting too tacked to the idea that there's one correct answer, like that's what brings meaning. That's my goal anyway.
I don't think there's a better way to end it, Andrew. I really appreciate that you would come down and contract your space-time and focus on this conversation for a few hours. It is a huge honor. I'm a huge fan of yours, as I told you. I hope you keep growing and educating the world about the human mind. Thanks for talking today.
Thank you. I really appreciate the invitation to be here. And people might think that I'm saying it just because I'm here, but I'm a huge fan of yours. I send your podcast to my colleagues and other people. And I think what you're doing isn't just amazing, it's important. And so thank you.
Thanks for listening to this conversation with Andrew Huberman, and thank you to our sponsors. A-Sleep, a mattress that cools itself and gives me yet another reason to enjoy sleep. SEM Rush, the most advanced SEO optimization tool I've ever come across. And Cash App, the app I use to send money to friends. Please check out these sponsors in the description to get a discount and to support this podcast. If you enjoy this thing, subscribe on YouTube, review it with 5 stars on Apple Podcasts, follow on Spotify, support on Patreon, or connect with me on Twitter at Lex Fridman. And now, let me leave you with some words from Carl Jung. I am not what happened to me. I am what I choose to become. Thank you for listening and hope to see you next time.